Hello there and welcome to Life Beyond Scene, where curiosity gets cozy and science takes the scenic route to slumber. Tonight our gentle dive isn't through stars or theories, but into the great expanse beneath our feet, or rather beneath the rolling blue that covers most of our planet. We're talking about the ocean, the place we all think we know, with its waves and its beaches, with its shells collected at low tide, with its smell of salt on the breeze. But the truth is we've barely touched it. The ocean is Earth's great hidden library, sealed shut by forces that keep us at the surface, peeking in without ever really reading the pages. And that raises the question that will guide us tonight. Why can't we truly explore the ocean? Why, in a time when we can land robots on Mars and photograph galaxies billions of light years away, does the vast body of water right here on Earth remain more mysterious than the farthest stars? Before we sink too far into the depths, I'd love to ask you something, just as we always do when we begin these slow wanderings. Where are you listening from tonight? Are you near the ocean, perhaps within earshot of waves curling onto the sand? Or are you landlocked, hundreds of miles away from the nearest shore? Have you seen the ocean in person, or is it still something you've only encountered in images and imagination? For some of us, it's a constant presence. For others, a rare and almost mythical landscape. Wherever you are, you're connected to it. Every sip of water you drink, every breath you take that owes its oxygen to marine plants, every weather pattern above your head, all of it ties back to those deep blue spaces we cannot fully enter. If you find comfort in these voyages, if the questions soothe you while they spark quiet wonder, I'd be deeply grateful if you gave this video a like, maybe subscribed, maybe even shared it with someone else who could use a calm corner of curiosity. It helps this space reach others who might need to drift off to science instead of stress. But whether you do or don't, you're welcome here as we let thoughts ripple out like waves, never in a hurry, always curious. So, let's begin. The ocean is the largest single feature on our planet, more than 70% of Earth's surface. When we look at a globe, we see continents. But what's really striking is how small they are compared to the watery wilderness between them. And yet, despite this dominance, our knowledge of the ocean is astonishingly thin. If you gathered up all the maps of the ocean floor produced so far, they wouldn't match the resolution we have of Mars or the Moon. The irony is hard to miss. We know more about the landscapes of barren, airless rocks in space than we do about the seafloor that lies just a few kilometres beneath ships crossing the waves. Why is that? Why does the nearest unknown remain the hardest to reach? Part of the answer lies in how we imagine distance. Space seems impossibly far away, but in some sense it's open. Once you build the right kind of rocket and survive the launch, space is vast but empty. There isn't air pressure crushing down on you. There isn't water tugging at every joint. There aren't currents pushing you off course. The ocean, by contrast, resists you from the first metre down. It presses against you with invisible weight. It swallows light, erases warmth, muffles sound. The deeper you go, the more it seems to say, this place is not yours. And unlike the infinite openness of space, the ocean feels close, almost haunting. You can stand on a beach, watch the horizon curve, smell the salt and hear the waves, but even 100 metres out you're already in a world that demands respect, and a few kilometres down you're in conditions that human beings can barely even simulate. When we speak of the ocean, we often picture its surface, boats bobbing, gulls crying, waves rolling. But that's only the thinnest film of what it really is. Imagine peeling away that glittering surface and sinking slowly into the depths. You pass through layers as if moving through worlds stacked atop one another. Sunlight filters down at first, illuminating fish and coral and forests of kelp. Then, gradually the light fades until there is only dim blue, then darker shades, then blackness complete. This isn't like turning out the lights in a room. It's a depth of darkness where light itself cannot survive, absorbed and scattered until it vanishes. And in that realm, where our eyes are useless, life continues in shapes and strategies we can barely comprehend. For most of human history, The ocean was both provider and terror. It gave food, it gave routes of travel, but it also swallowed ships whole and hid monsters in imagination. Fishermen might know the shallows, sailors the surface, but the deep was left to myths. Sea serpents, krakens, vast beings with tentacles that could wrap around ships, these filled the void of knowledge. And in a way, those myths were acknowledgements of truth. The deep ocean is alien, as foreign to us as any distant planet. And until very recently, it was as unreachable. Even now, with all our technology, the barriers are daunting. The pressure at the deepest part of the ocean is over 1,000 times what we experience at the surface. Imagine the weight of an entire adult elephant pressing on every square inch of your body. That's the reality a submersible faces as it descends into trenches like the Mariana. Our materials, our machines, our bodies themselves struggle against forces that seem almost designed to keep us out. And pressure is only the beginning. Cold, darkness, and distance all conspire to make exploration difficult. We've sent probes to the bottom, we've built submersibles strong enough to withstand the crushing depths, but these are rare, expensive, and often short-lived ventures. Each dive is like sending an expedition to another world. It takes years of preparation, millions of dollars, and still carries enormous risk. Compare that with sending a satellite into orbit, where once it's aloft it can circle the planet for decades, transmitting data. The ocean doesn't give us that. It demands constant effort just to exist within it, let alone measure and map. And yet, we keep trying. We send sonar pings that bounce back from the seafloor, sketching its outlines in broad strokes. We launch autonomous robots that glide silently through mid-water, recording temperature, salinity, and currents. We lower cameras into the abyss, their beams catching glimpses of creatures that look more like imagination than biology. Each piece adds to our map, but the picture remains frustratingly incomplete. The ocean always holds more than we've seen, more than we've measured, more than we've even guessed. So tonight, as we drift gently into this question, we'll move slowly through the barriers that keep us from truly exploring the ocean. We'll talk about pressure, darkness, cold, currents, strange creatures, human limits, fragile technology, and the sheer expense of curiosity. We'll see how myths and fears mirror the real challenges, and how the ocean shapes not just our planet, but our imagination. And along the way, we'll remind ourselves that the unknown isn't always far away in the stars. Sometimes it's right here, under the waves, just out of reach. Now that we've settled into this journey together, let's drift into the first part of our ocean wandering. We often talk about the ocean as though it's a familiar place, a backdrop to vacations, postcards, or summer afternoons at the beach. For many of us, the ocean is waves rolling in and out, foamy edges kissing the sand, the smell of salt and sunscreen mixed in the air. It's children building sandcastles, couples walking hand in hand along the shore, surfers waiting for the next good swell. And so, we imagine we know the ocean. We look at its surface and think, yes, this is the sea, I've seen it, I understand it. But the truth is that what we see is only a thin skin stretched across something unimaginably vast. The surface is the cover of a book we've barely cracked open. Stand on a beach anywhere in the world, and it's easy to feel like the ocean is a single place, uniform in its rolling, glittering waves. But beneath that surface are landscapes more diverse and more dramatic than anything on land. There are mountain ranges taller than the Rockies hidden beneath miles of water. There are canyons deeper than the Grand Canyon winding across the seafloor. There are plains, plateaus, volcanic ridges and trenches that could swallow Mount Everest whole and still leave room for another mountain. The scale is staggering, but because it's hidden underwater, we tuck it away as though it doesn't matter. We go on imagining that the ocean is just a blue flatness between continents, something to cross with ships or admire at sunset. The illusion of familiarity comes from distance. We see only what the ocean shows us at its edges, and our brains quietly fill in the rest with assumptions. The funny thing is, most of us experience the ocean in ways that encourage this illusion. A beach holiday shows us only the shallowest shallows. A boat ride keeps us bobbing on the surface. Even documentaries, as dazzling as they are edited glimpses from carefully planned expeditions, often in relatively accessible waters. These fragments become the story we carry in our heads. We imagine that the sea is fish swimming in schools, dolphins leaping, whales breaching, corals blooming like underwater gardens. And yes, those things are true, but they are only 1% of the story. The rest remains hidden in the dark, cold, pressurized spaces we cannot reach. It's worth thinking about how much our language contributes to this sense of knowing. We talk about the ocean as though it's one thing, a single body of water. Technically, it is all connected, a continuous volume that wraps around the globe. But in reality, the Atlantic, Pacific, Indian, Arctic and Southern Oceans all have their own currents, climates and ecosystems. They are vast, distinct and dynamic. Yet we often lump them together as if saying ocean settles the matter. Imagine if we spoke about land in the same way, saying the land as though a desert, a rainforest and a mountaintop were the same. That's the kind of oversimplification we make every time we talk about the sea. And then there's the fact that we live on the tiny portion of Earth not covered by water. More than 70% of the planet's surface is ocean, and yet the overwhelming majority of humans live on land, near coasts or rivers, but rarely venturing far beyond. Our maps are land-centred, our stories land-centred, our history land-centred. The ocean becomes the empty space between the dots of civilization, when in fact it is the main stage. Life began in the ocean, climate is regulated by the ocean, and the oxygen you're breathing right now is largely generated by microscopic plants floating in the sea. We treat it like a border, when in truth it is the foundation. It's also easy to forget how little of it we've seen. Some estimates say that less than 20% of the seafloor has been mapped in detail, and even that mapping is often from sonar scans taken from ships on the surface, not from direct observation. The percentage of the deep sea we've actually visited with cameras or submersibles is tiny, less than 1% of the whole. That means that most of the ocean, most of our own planet, is completely unobserved, unknown and unexplored. If you're picturing dark patches on a map labelled "Here be dragons," you're not far off. In fact, medieval maps often filled the edges of the known world with sea monsters. Perhaps it wasn't so much ignorance as honesty. They didn't know what lay beyond, and to some degree neither do we. This gap between perception and reality gives the ocean a strange dual identity. On the one hand, it's familiar and comforting. We picnic by it, swim in it, surf on it, and build entire economies around seaside tourism. On the other hand, it's alien and forbidding. A person standing waist deep in the shallows is inches away from an environment that, within a few hundred meters, becomes utterly uninhabitable. That line where your toes lose contact with the sand, where the seafloor drops away and you begin to float, that's the beginning of a frontier as foreign as the surface of the moon. Our relationship with the ocean has always been shaped by this illusion of knowing. Ancient cultures respected it, feared it, worshipped it, and mythologized it, but few understood it beyond the surface. Sailors charted courses across it. Fishermen learned its rhythms, but even they only scratched at the edges of a mystery. The illusion continues today with technology. We can fly drones across battlefields on the other side of the world, stream high-definition video from space stations, and yet when it comes to the ocean, our tools often fail just a few kilometers down. We assume mastery because we've mastered so much else, but the sea humbles us again and again. Think for a moment about the last time you looked out across the water. Maybe it was from a pier or a ferry, maybe from the deck of a cruise ship, maybe from a cliff top looking down at the surf. That horizon where the sky meets the sea seems solid, something you can almost touch. But everything beyond that line is unknown territory. We don't know what creatures swim beneath, what ridges rise, what trenches yawn. The illusion is that the horizon marks the end of knowing, when in fact it marks the beginning of ignorance. And yet, there's a kind of comfort in this illusion. If we truly grasp the scale of the unknown beneath the waves, it might be overwhelming. Entire civilizations have lived and died with only the faintest idea of what lay below the surface. Our ancestors crossed oceans in wooden ships, navigating by stars and luck, with no knowledge of the worlds hidden beneath their keels. Even now, as aircraft trace lines overhead and satellites beam signals back and forth, most of what lies under the waves remains untouched. The ocean is the closest thing we have to a true wilderness, and perhaps that's part of why it retains its mystique. Still, the illusion carries dangers. Believing we know the ocean has led us to treat it carelessly. We dump waste into it, overfish its populations, warm it with emissions, acidify it with pollution. We assume that something so vast will absorb our mistakes, when in fact it is fragile in ways we're only beginning to understand. The illusion of familiarity makes it easy to think of the ocean as endless, but it is not. Its ecosystems are intricate, its balance is delicate. The more we assume we know, the more harm we risk causing without realizing it. So, when we say the ocean is familiar, we're speaking from the surface. We're speaking as land creatures, looking at the waves and projecting our own comfort onto them. But peel back that surface, even a little, and the illusion cracks. The sea reveals itself as a world unto itself, layered and vast, alien and essential. We are land dwellers standing on the edge of a frontier, pretending we've already crossed it. And as we move deeper into our story tonight, we'll begin to see how quickly that illusion fades once we descend, how every metre of depth brings new challenges, how every attempt to explore reveals more of what we don't know. When we think of distance, we usually picture horizontal space, a road stretching away, a flight across continents, a rocket leaving the atmosphere and heading into orbit. Distance is measured in how far we move across a map, in miles or kilometres we can trace with a finger. But the moment we turn that concept downward into the ocean, something strange happens. Depth, though measured in numbers that look small next to the reaches of space, feels immeasurably far. A few kilometres of water is more daunting than millions of kilometres of vacuum. Down feels farther than out, and the reasons why tell us a great deal about why the ocean remains unexplored. On paper, it doesn't make sense. The International Space Station circles Earth at around 400 kilometres above the surface. The Moon is nearly 400,000 kilometres away. Mars, depending on orbits, is tens of millions. Compare that to the Mariana Trench, the deepest part of the ocean, which drops just under 11 kilometres. 11 compared to millions seems laughably small. Yet ask most people which feels more accessible, sending a probe to Mars or to the bottom of the trench, and the instinctive answer often leans toward Mars. We've sent rovers there. We have photos, data, even plans for future astronauts. But the deepest parts of our own ocean have been visited only a handful of times in all of history. That disparity isn't just about numbers, it's about how depth warps our perception of distance. When we look up at the sky, there's openness. We know space is hostile, but it's also empty. Once you escape the pull of gravity and survive the initial violence of launch, you are coasting. There are challenges, but they're the kind of challenges machines can handle in long arcs of orbit or interplanetary drift. Looking down into the sea, however, every metre resists. Water is heavy, and the weight stacks with each passing metre. At the surface you barely notice it, but by 100 metres down the pressure is already 10 times greater than at the beach. By 1,000 metres it's crushing, by 10,000 it's beyond comprehension. The ocean's resistance doesn't spread out over millions of kilometres. It piles up directly on top of you, making even a short vertical distance feel impossible. Part of why depth feels so remote is that we can't see it. Stand outside on a clear night and look up. The stars may be impossibly far, but you can still glimpse them. You can trace the arc of satellites, Watch the International Space Station pass overhead like a bright dot racing through the sky. Space reveals itself to our eyes even from the ground. The ocean does not. Peer into the water and your vision ends within meters. Light is absorbed and scattered, so the sea hides itself. That concealment makes depth feel infinite. The unknown starts right at the surface, and it thickens with every descent. Even shallow diving reminds us of this. At 20 or 30 meters, sunlight is dimmer. Colours fade. Red vanishes first, then orange, then yellow, until everything is blue and grey. The very physics of light conspires to erase familiarity, and what you can't see stretches the imagination into infinity. There's also a psychological trick at play. Humans evolved on land, where down means safety. Gravity pulls us toward the ground, and the ground holds us. Depth in air doesn't threaten us in the same way. Go down a mountain, descend into a valley, and you remain in the open air, breathing freely. But in water, down means leaving behind what sustains us. The deeper you go, the farther you are from air. That reversal of instinct, where down is no longer secure but lethal, magnifies our sense of distance. It's not just how far it is, it's how quickly survival becomes impossible. This is why space and sea invite such different emotions. Space can feel inspiring, a canvas of possibility. The ocean can feel claustrophobic, pressing, suffocating. Astronauts talk about the overview effect, the awe of seeing Earth from above, the beauty of the blue marble suspended in blackness. Divers talk about the silence, the cold, the disorientation of descending into darkness. Both are extraordinary, but one is framed as expansion and the other as encroachment. Depth feels farther, because it feels like the world is closing in rather than opening out. Another reason down feels farther than out is speed. A rocket to orbit takes minutes to reach space. Probes slingshot to other planets in months or years, but the launch itself is fast. By contrast, a descent into the deep ocean is painfully slow. Submersibles crawl downward at a pace measured in meters per minute. A journey to the deepest trench can take hours, and in that time the pressure increases relentlessly. You are not leaping into the unknown. You're lowering yourself into it inch by inch, hearing the groans of metal, feeling the temperature drop, watching the light disappear. That slowness makes every kilometre feel longer than the thousands that separate us from the moon. Consider also how few have actually gone there. Spaceflight is rare, but thousands of people have been to space in some form, orbiting, working aboard stations, even tourists in recent years. The deep trenches, by contrast, have seen fewer visitors than the surface of the moon. When filmmaker James Cameron descended in 2012, he joined a club of just a handful of explorers. Each attempt was experimental, risky, and costly. The sheer rarity of these dives reinforces the sense that depth is more remote than space. There's a cultural angle too. Space exploration has always carried a sense of glory. Nations race to plant flags, companies advertise ambitions, movies and television dramatize adventures among the stars. The ocean, though, is framed differently. Shipwrecks, disasters, storms, submarines lost without trace. These dominate the stories we tell about the deep. One frontier is celebrated as the future, the other as a graveyard. That shapes how we perceive distance. Outward feels heroic, downward feels foreboding, even if the actual numbers don't justify the difference. Think about how maps reinforce this as well. Space is drawn outward with scale bars that stretch for millions of kilometres, a vastness that becomes abstract. The ocean is shown as a blue wash, with a few contour lines indicating depth. We don't see the trenches and ridges the way we see continents and planets. Without visualization, our minds translate depth into mystery, and mystery into distance. If the seafloor were drawn on maps with the same detail as Martian canyons or lunar craters, we might think of it differently, but because it's hidden, we imagine it as farther than it is. there's also the issue of human frailty. In space, once a spacecraft is functioning, the humans inside can live for months. They recycle air, grow plants, exercise in zero gravity. In the deep sea, life support is measured in hours. A submersible has limited oxygen, limited power, limited tolerance for error. The margin between safety and disaster is razor thin. That fragility makes each kilometre downward feel more dangerous, more distant. Even though the actual distance is small, the risk per metre is immense, and our minds conflate risk with remoteness. And here's something else: the way sound travels. In space there is silence, but radio signals move freely. A rover on Mars can send pictures across millions of kilometres. In the ocean, sound travels better than light, but it bends, echoes, and distorts. Communication with submersibles is patchy, delayed, sometimes impossible. That disconnection makes depth feel isolated in a way even the far side of the moon is not. You can phone home from space. From the deep sea, you are cut off. That sense of isolation makes the bottom of the ocean feel farther than orbit. All of this combines into a paradox. The ocean is right here. It touches every continent, laps at every shore. Children splash in it, sailors cross it, surfers ride its waves. And yet its depths are so inaccessible that we think of them as farther away than worlds that lie millions of kilometres beyond our planet. Depth bends our sense of distance, turning kilometres into impossibility. That's why down feels farther than space, and it's one of the central reasons the ocean remains unexplored. But of course depth is not just perception. The challenges that make it feel far are real. The pressure, the darkness, the cold, the currents. These are not illusions. They are physical barriers that resist exploration at every step. And so, as we continue, we'll leave behind the sense of distance and begin to talk about the forces themselves, starting with the weight of the ocean pressing downward, the invisible hand that keeps us from sinking too far into its world. When you stand at the edge of the sea, maybe ankle deep as the waves wash around you, it feels weightless. The water buoys you, lifts you, makes you lighter than you are on land. Children float on inflatable rings, swimmers glide forward with little resistance, divers sink gently through clear shallows. It's easy to imagine that water removes weight, but this sensation is a trick of the surface. The ocean is not light at all. It is heavy beyond anything we normally experience, and its weight grows relentless with every metre down. Pressure is the invisible barrier that guards the deep, the force that has crushed more dreams of exploration than any monster of myth ever could. To understand this, it helps to think about what pressure really is. On land, we live under atmospheric pressure, the weight of the air stacked above us. We don't feel it because our bodies are balanced against it, every cell pushing outward as much as the air pushes inward. At sea level, that pressure is about 1 kilogram on every square centimetre of your body. It sounds trivial, but multiply it across the surface of your skin, and it adds up to the weight of a car pressing on you at all times. We simply don't notice because it's always been there, constant and familiar. But water changes the game. Water is much denser than air, and it doesn't take kilometres of it to add weight. Just 10 metres below the surface, you already feel an extra atmosphere of pressure, another entire car pressing on every square centimetre. At 20 metres, 2 cars. At 30, 3. And so it continues, each 10-metre descent stacking more invisible vehicles onto your body. For a recreational diver, this is part of the thrill. At a few metres down, you can feel the squeeze in your ears, the mask pressing gently on your face. You equalise, blow air into spaces that would otherwise collapse, and you continue downward. At 30 or 40 metres, your lungs are compressed to half their surface volume, your buoyancy shifts, and you become heavier in the water. Still, with training and equipment, you can move comfortably. But beyond those depths, things change quickly. For a submarine or a deep-sea probe, the numbers mount in ways that defy ordinary imagination. At 1,000 metres, The pressure is 100 times greater than at the surface. At 10,000 meters, at the bottom of the Mariana Trench, it is over 1,000 times greater. Each square centimetre of a hull must withstand the weight of an elephant, and there are countless square centimetres. The ocean is not just heavy, it is absolute, relentless, all-encompassing. This is why building machines for the deep is so difficult. On land, you can construct towers kilometres tall, bridges spanning vast rivers, rockets to space. These marvels contend with gravity, wind, heat, and vibration, but not with a force that presses equally from all sides without pause. A submarine hull must be perfect. One weakness, one imperfection in the weld, one bubble in the metal, and the result is catastrophic. Implosions at depth are not slow. They're instantaneous. A craft fails, and in milliseconds it is reduced to fragments. Engineers know this, which is why the vehicles that descend far below are shaped in the simplest form possible, spheres. A sphere distributes pressure evenly across its surface, resisting collapse more effectively than any other shape. That's why the tiny cabins that carry humans into the abyss are round, bolted shut, and small enough to feel claustrophobic. It's not comfort that decides the design, it's survival. Even so, the risk is never zero. Every descent into the deep sea carries with it the knowledge that failure means instant death. This is not melodrama, it is physics. The most famous example in recent memory came when a private submersible collapsed during an attempt to visit the Titanic wreck. The pressure at those depths gave no time for alarm, no chance for rescue. For explorers and engineers, it was a grim reminder that the ocean does not forgive mistakes. The deeper you go, the less margin there is for error, and the more absolute the consequences become. Pressure doesn't only affect machines, it also limits what living things can do. Human bodies, fragile in their design, can only go so far before tissues begin to fail. Divers who attempt to reach extreme depths must breathe carefully controlled gas mixtures, not ordinary air. At high pressure, nitrogen becomes narcotic, producing a dreamy intoxication that can cloud judgment. Oxygen too, safe and essential at the surface, becomes toxic when compressed beyond certain limits. Breathing at depth is a balancing act of chemistry, and mistakes are costly. Professional divers who work on undersea structures sometimes spend days in pressurized habitats, their bodies saturated with gases that would be lethal at the surface. When they finally return, they must decompress slowly, rising in stages, allowing gases to escape their blood without forming bubbles. Skip this process, and the result is the bends, where nitrogen expands inside the body, causing pain, paralysis, even death. Pressure reshapes not only metal but flesh. Other creatures, however, have found ways to thrive. The deep ocean is full of beings adapted to environments that would kill us instantly. Fish with flexible skeletons, gelatinous bodies, and specialized proteins that keep cells functioning under crushing loads swim casually where human machines dare not go. Some organisms produce antifreeze-like chemicals. Some rely on slow metabolisms that use little energy. Some collapse their lungs entirely and use dissolved oxygen in their blood. Where we see impossible pressure, evolution has produced resilience. The contrast is humbling. We need spheres of titanium and composite to descend. They need only the quiet inheritance of countless generations. Still, even these creatures have limits. The very deepest trenches host fewer species than the shallower zones above. At a certain point, the weight becomes so immense that only the most unusual life persists. Scientists debate whether there is an absolute limit, a depth beyond which no multicellular organism can survive. If so, the ocean may contain its own boundary, a frontier not only for humans but for life itself. The thought is both eerie and profound, a reminder that the planet's greatest wilderness may also be its most constrained. Pressure has another consequence. It makes exploration expensive. A rocket to space is costly, but once launched it operates in emptiness. A deep-sea submersible must withstand crushing forces at every moment. Materials must be tested to perfection, hulls built to exacting standards, systems designed with redundancies. The cost of failure is so high that safety margins are immense, which drives up price further. This is why so few nations or companies invest heavily in deep exploration. It's not just difficult, it's financially punishing. For every dive to the trenches, there are hundreds of satellites in orbit. The economics reflect not just ambition but physics, and yet the lure remains. Scientists want to know what lies in the deep because it is still unknown. Pressure may crush machines, but it also hides secrets. Hydrothermal vents, where mineral-rich water spews from the crust, host entire ecosystems without sunlight. Vast pools of brine heavier than seawater form lakes at the bottom of the sea, complete with shorelines and waves. Gigantic squid, once the stuff of sailors' stories, have been filmed alive in the deep. Each discovery proves that what pressure hides is worth uncovering. The challenge is building machines strong enough to endure long enough to observe. The strange thing is that pressure is invisible. You can't see it the way you see waves or currents. A diver descends, a submersible sinks, and the water looks the same. But every centimetre is heavier than the one before. The ocean's weight is silent, patient, and absolute. It doesn't roar like a storm or crash like surf. It simply exists, pressing evenly from every side, waiting. That silence is part of what makes it eerie. Space has emptiness. The sea has fullness. And fullness can be more dangerous than void. For humans, pressure also carries psychological weight. Imagine sitting inside a steel sphere 2 meters wide, bolted shut, descending for hours into blackness, knowing that just beyond the walls are force weights that could obliterate you instantly. The hum of pumps, the creak of metal, the faint hiss of air circulation become magnified in the mind. Every sound could be a warning, every vibration could signal failure. Explorers speak of the tension, the awareness that they are visiting a place that does not tolerate their presence. To descend under pressure is to enter not only a physical challenge, but a mental one, and yet people continue to go. Perhaps it is stubbornness, perhaps curiosity, perhaps the same drive that once carried humans across deserts and mountains and eventually into space. We are drawn to frontiers, and pressure, though invisible, marks one of the clearest frontiers we face. To conquer it is to prove that we can step beyond the limits imposed by nature, even if only briefly. Each successful dive is a statement that pressure can be endured, that knowledge can be wrestled from the deep despite the weight pressing against us. The irony is that we live under pressure all the time. Our bodies are balanced against the weight of the air, so we forget it. But go down into the ocean, and the balance shifts. The reminder is immediate and unforgiving. Pressure is not an exotic force. It is the most ordinary one, amplified beyond recognition. It is the familiar made hostile. And in that hostility lies the greatest reason we have not truly explored the ocean. Of course, pressure is only one part of the story. It works hand in hand with darkness, with cold, with currents, with distance. It guards the deep like a gatekeeper, but beyond that gate lie other challenges waiting. If pressure squeezes the life from our machines and our lungs, then darkness robs us of vision, turning the deep into a world where light itself cannot survive. To understand why the ocean is so hard to explore, we have to pass from weight into shadow, from the crushing embrace of water into the endless night where sight disappears and other senses must take its place. If pressure is the ocean's first great barrier, then darkness is its second. The two arrive together, inseparable, as you leave the surface behind. Light penetrates water only so far, and beyond that, sight itself ceases to function. On land and in space, vision is our primary sense. We map, explore, and understand by looking. We take pictures, we scan horizons, we orient ourselves with stars. In the deep ocean, that tool is stripped away. Darkness rules. Not the gentle dimming of dusk, not the familiar black of a bedroom with curtains drawn, but a depth of darkness so complete that the very concept of colour disappears. It is not just absence of light, it is the absence of possibility for light. At first, the descent feels almost normal. In the upper layers of the sea, sunlight still filters through. Swimmers, snorkelers, and divers play in a zone called the euphotic, or good light zone. It extends to around 200 metres, which sounds deep until you realise it's less than 1% of the average ocean depth. In this layer, fish flash silver in the sun, coral reefs explode with colour, and photosynthesis still fuels life. This is the ocean most of us picture, because it's the only one we've truly seen. But below it lies the twilight zone, where light dwindles to dim blue and eventually vanishes. By 500 metres, the sun is gone. You could lower a lamp into the water and watch its glow fade within a short radius, swallowed by the black. By 1,000 metres, the ocean is utterly lightless. This is the midnight zone, and below it, even deeper, the abyss and the trenches stretch into total darkness. No human eye, unaided, can see anything here. The ocean has swallowed not just light, but the very idea of sight. This is a profound obstacle for exploration. Our machines, like us, are built around vision. Cameras, lights, lenses, these are our go-to tools. But in the deep sea, they are handicapped. Shine a light and the particles suspended in water scatter it back, turning the beam into a blinding fog. The more powerful the lamp, the more backscatter you create. Submersibles often resemble moving orbs of faint light surrounded by impenetrable black, like lonely fireflies in a void. The field of view is small, the sense of scale impossible. Unlike the open vistas of space, the deep sea never shows you more than a tiny patch of itself. Exploration here is like wandering a vast cathedral at night with only a candle. The darkness also changes how sound and light interact. In space, radio waves cross the void. In the ocean, sound is king. Whales call across thousands of kilometres. Submarines rely on sonar to map and navigate. Scientists send pings downward, listening to echoes that reveal the shape of the seafloor. But sonar is a crude substitute for sight. It tells you distance, shape, density, but not colour, not detail, not the small flicker of life. It's like trying to understand a painting by tapping it with a stick. Darkness forces us into clumsier senses, leaving us blind in ways we rarely confront elsewhere. For life itself, darkness is both a limit and an opportunity. Without sunlight, photosynthesis stops. Plants cannot grow, algae cannot bloom, the energy chain that fuels surface ecosystems breaks. Instead, the deep ocean depends on other sources. Some rely on the slow rain of organic material from above, particles drifting down through the black. Others cluster around hydrothermal vents, where chemical reactions replace sunlight as the fuel for life. Still others have evolved a magic trick: bioluminescence. Bioluminescence is light created by living organisms, and in the dark ocean, it is everywhere. Tiny plankton flash when disturbed, making trails of light behind swimming fish. Predators dangle glowing lures to attract prey. Squid eject glowing clouds instead of ink to confuse attackers. Entire schools of creatures pulse in coordinated displays, like galaxies in miniature. To descend into this world is to enter a star field upside down, stars made not of plasma, but of biology. Bioluminescence is not rare. Scientists estimate that the majority of deep-sea species can produce light in some form. The deep ocean may be dark, but it is far from invisible. It glitters in ways the surface world barely imagines. For humans, encountering bioluminescence is one of the most surreal experiences possible. Imagine sitting in a submersible, lights turned off to save power, staring into blackness, when suddenly the water outside blooms with living sparks. Trails of green, blue and white weave and vanish. Creatures drift by carrying lanterns within their own bodies. It is alien and beautiful, yet utterly natural. These flashes remind us that while our vision fails, evolution has filled the gap with its own inventions. But here too lies a barrier. Cameras can capture bioluminescence, but only with difficulty. The flashes are brief, the light faint, and artificial lamps often drown them out. To see the natural glow of the deep, explorers must turn off their lights and sit in darkness, waiting, watching, hoping for life to reveal itself. This patience doesn't fit well with our usual ways of exploring. We are creatures of light, used to shining beams and expecting immediate images. The ocean forces us to slow down, to accept blindness, to trust that something may appear in its own time. Darkness also shapes how we feel about the deep. Humans fear what they cannot see. On land, darkness at night still carries echoes of ancient dangers, predators hiding, threats unseen. In water, the fear is amplified. We know creatures are there, but we cannot see them. The blackness feels infinite, swallowing not just vision but certainty. Every sound becomes suspicious, every shadow imagined. Divers describe the uncanny sensation of knowing they are surrounded by life but being unable to perceive it. That unease is another reason the ocean feels harder to explore than space. Space may be empty, but the sea is full of things we can't see, full of shapes and movements hidden in darkness. The problem is not just perception, but practicality. Darkness makes mapping slow. It makes photography challenging. It makes navigation hazardous. Submersibles must bring their own light, but light means power, and power is limited by batteries. Each mission is a trade-off. How much energy to spend on propulsion, how much on instruments, how much on illumination. Every extra lamp is less time underwater. Exploration becomes a balancing act, constrained not by distance but by darkness. And yet, paradoxically, the darkness is part of the appeal. Scientists, filmmakers and adventurers alike describe the wonder of entering a world so completely unlike the surface. It is a reminder that our planet holds realms as strange as any science fiction setting. A reminder that we share Earth with ecosystems we barely understand. Darkness protects these places, slows our intrusion, forces us to work harder for each glimpse. It is frustrating, but also humbling. The ocean keeps its secrets not out of malice, but simply because light cannot follow us there. To imagine the scale of this hidden world, picture Earth without oceans, drained of water. Mountains and valleys, ridges and trenches would stretch across its surface. Now cover it again with liquid darkness, and realize that 90% of it will never feel sunlight. This is not a small corner of the planet. This is most of the planet. Our familiar sunlit world is the exception. Darkness is the rule. The fact that we live in the rare slice of Earth where light exists may be the real anomaly. Technology is improving, of course. Autonomous vehicles equipped with sensitive cameras, sonar and other instruments venture into the dark more often than before. Some use red lights, invisible to most deep-sea creatures, to avoid disturbing them. Others rely on incredibly sensitive sensors that can detect faint glows invisible to human eyes. But these are still partial solutions. Darkness remains the defining feature of the deep. To explore it fully would require not just new tools, but a shift in how we imagine exploration itself. We must accept that some things cannot be lit up easily, that some worlds must be felt, heard, and waited for rather than brightly seen. Perhaps this is why the ocean feels more mysterious than space. Space dazzles with visible stars, galaxies, and planets. The ocean hides. It begins its concealment just meters below the surface, where even sunlight cannot penetrate fully, and then it holds that concealment across most of the globe. Darkness is not an occasional feature, it is the ocean's identity. And as explorers, that forces us to admit our dependence on light, our bias toward vision and our discomfort when both are taken away. Still, we go, because even in darkness we discover. A glowing jellyfish drifting past, a strange fish with transparent head and tubular eyes, a shrimp snapping claws that create flashes of heat and light. All of these are real, seen in brief encounters in the dark. Each discovery is a reminder that life has adapted to conditions we find unlivable, that nature thrives where we would perish. Darkness may hide, but it does not erase. The ocean is alive in its blackness, and the challenge for us is learning how to share that world without flooding it with intrusive beams. And so, as we leave this part of the journey, we carry with us the understanding that the ocean is not just deep, not just heavy, but profoundly dark. It is a darkness that resists, a darkness that shapes life, a darkness that humbles explorers. The farther we go down, the more it surrounds us, until it becomes clear that we are visitors in a world where sight is not the rule but the exception. From here, our path leads into cold, the chill that creeps alongside the dark, a cold that seeps into everything, machinery and body alike, reminding us that in the deep ocean, warmth is as scarce as light. If darkness strips the ocean of light, then cold strips it of warmth. Together they create an environment so alien it's difficult to reconcile with the images we carry of the sea as a place for swimming, sailing, and summer holidays. The truth is that most of the ocean is cold beyond anything we usually experience. It is not the refreshing chill of dipping into a lake, not the bite of winter wind against your skin, but a near-freezing stability that defines the vast majority of the deep. Scientists often describe it in numbers, 2 to 4 degrees Celsius, hovering just above freezing, but numbers fail to capture the reality. Imagine living in a refrigerator not for a moment but forever, with no fire, no sun, no seasons, no reprieve. That is the ocean's frozen heart. At the surface, things are different. Sunlight warms the first few meters, sometimes tens of meters, depending on currents and location. This thin layer changes with the seasons, warming in summer, cooling in winter, stirred by storms. It's the layer most people interact with, so it creates the illusion that the ocean is dynamic in temperature, shifting the way the air does above land. But beneath that surface veneer lies the thermocline, a region where temperature drops rapidly with depth. Descend a few hundred meters and the warmth vanishes. By 1,000 meters you've entered a world that might as well be eternal winter. 90% of the ocean lies in this cold zone, untouched by the fluctuations above. For humans, cold is not just uncomfortable, it is dangerous. Our bodies rely on a narrow range of temperatures to function. Fall below that range and systems begin to fail. Muscles weaken, nerves slow, organs shut down. Even a brief swim in cold surface waters can sap energy quickly. Hypothermia sets in, sometimes within minutes, and survival becomes a race against time. That's just at the surface, in water around 10 degrees Celsius. In the deep, where temperatures are closer to 2, human exposure would mean near-instant incapacitation. The body simply cannot cope. Machines also struggle. Batteries drain faster in cold conditions. Materials become brittle. Lubricants thicken. Electronics slow. Deep-sea submersibles must be engineered not only to withstand pressure, but also to function reliably in constant cold. Every wire, every circuit, every moving part must be tested for resilience at low temperatures. A failure on the surface can be repaired. A failure in the abyss means the end of a mission, sometimes the loss of millions of dollars of equipment, and always the reminder that the ocean's chill is as unforgiving as its weight. Cold also shapes how life exists in the deep. Metabolism slows. Creatures conserve energy, moving less, eating less, reproducing less frequently. Many deep-sea species live long, slow lives, stretching decades or even centuries. A shark discovered in the Arctic was estimated to be nearly 400 years old, a lifespan almost unimaginable for a vertebrate. This longevity may be linked to the cold, which slows cellular processes and reduces wear over time. In a way, the deep sea preserves its inhabitants in a kind of suspended animation, a slower rhythm of existence adapted to the frozen environment. At the same time, cold can create strange paradoxes. Water at the surface freezes into ice, but in the deep sea, even at near freezing temperatures, liquid persists because of pressure. The immense weight of the water column prevents freezing, keeping the ocean liquid where on land the same temperature would mean solid ice. This balance of cold and pressure produces unique phenomena such as brinicles, icy fingers of death that form when supercooled. Salty water sinks from beneath sea ice, freezing everything it touches as it drifts downward. These fragile structures creep across the seafloor, encasing starfish and other creatures in ice. A lethal reminder that cold in the ocean can behave in ways we rarely see elsewhere. The cold is not uniform, of course. Pockets of warmth do exist, most dramatically around hydrothermal vents, where water heated by volcanic activity gushes into the surrounding chill. These vents create oases of life, where tube worms, crabs, and strange bacteria thrive in temperatures that would cook organisms from elsewhere. Yet even here, the balance is delicate. Just a few centimetres away, the water returns to near freezing. Life clings to the margins, adapted to both extremes, a testament to how adaptable and fragile existence in the ocean can be. For explorers, cold complicates everything. Cameras fog, instruments stiffen, and the risk of condensation damaging sensitive electronics grows. Protective housings must keep equipment dry and warm in conditions where warmth doesn't naturally exist. Even the act of bringing samples back to the surface becomes tricky. Creatures adapted to near-freezing darkness often die quickly when exposed to warmer, lighter conditions. Scientists struggle to study them alive, their biology so tuned to the frozen deep that our world becomes instantly lethal. The ocean guards its secrets not only with pressure and dark, but with cold that makes its inhabitants strangers to us. Culturally, cold has always symbolized distance, danger, and remoteness. Polar explorers in history fought frostbite, starvation, and despair in frozen landscapes. The ocean amplifies that symbolism by hiding its cold beneath an inviting surface. The sun can be blazing, the sand hot under your feet, but just a few meters below, currents bring icy water surging upward, numbing skin and shocking the body. It's a reminder that the ocean is never fully what it seems. Warmth above can disguise cold below, and the transition between the two can be abrupt. For ancient sailors with no knowledge of thermoclines or currents, these sudden chills must have felt uncanny, even supernatural. For modern science, they're a clue to the vast circulation systems that move heat around the planet. Indeed, the cold of the deep ocean is not just a local feature, it plays a global role. The movement of cold, dense water helps regulate climate, carrying oxygen to the depths and distributing heat around the world. The great conveyor belt of ocean currents, driven by temperature and salinity, links every sea into a planetary system. Without it, the climate would swing more wildly, ecosystems would collapse, and life on Earth would be unrecognizable. The cold heart of the ocean, though hostile to us, is essential for the stability of everything we know. And yet, despite its importance, this cold world remains mostly hidden from direct study. Our satellites can measure surface temperatures with precision. Our ships can drop probes that record temperature profiles as they sink. But to live and work in the deep cold is something we cannot yet do at scale. We send machines for brief visits, but we have no permanent outposts in the abyss. No laboratories sit on the seafloor. No observatories record from within the frozen dark. In space, we dream of colonies and stations. In the ocean, we barely dream at all, because the cold itself makes permanence unthinkable. This may be one of the reasons the deep sea feels less explored than space. It is not just that it is dark or pressurized. It is that it is relentlessly, unchangingly cold, a barrier that does not fluctuate with weather or seasons. You cannot wait for better conditions because they never come. You cannot plan for warmth because there is none. The deep is locked at near freezing, a timeless stability that refuses compromise. For explorers, this constancy is as daunting as any storm. And yet, as with pressure and darkness, the cold is also what makes the deep remarkable. Creatures glow against it, vents burn within it, and strange chemistry thrives because of it. The ocean's frozen heart is not lifeless, but alive in forms we barely comprehend. Its chill is both enemy and architect, shaping ecosystems unlike any on land. For us, it is a challenge. For the ocean, it is simply the way things are. When we talk about why the ocean cannot be fully explored, we must remember that cold is not a minor inconvenience but a defining feature. It limits what we can do, how long we can stay, what survives the journey back. It slows life, hinders machines, and creates conditions that are utterly alien to our warm-blooded biology. It is not dramatic in the way storms are, not sudden in the way tsunamis are. It is quiet, constant, unyielding. It is the background state of most of the planet, and perhaps that's what makes it hardest for us to accept. We like change, cycles, seasons. The ocean offers permanence, and that permanence is near freezing cold. As we move onward in our slow journey tonight, we leave the cold as a reminder that the ocean is not a place built for us. It is built for itself, for life that has adapted across millions of years to pressure, darkness, and chill. We are visitors, fragile and temporary, and each barrier we meet reminds us how small our presence really is. But the barriers do not end here. Alongside the cold move the waters themselves, currents and chaos invisible to our eyes, shifting rivers that run within the sea, complicating every attempt to map or measure. The ocean is not still. It moves endlessly, and in that movement lies another reason why exploration slips from our grasp. When you look out across the ocean from the shore, it seems like a single body, stretching away in every direction. The waves rise and fall, the surface glitters, and it all looks deceptively uniform. But beneath that surface, the water is never still. It moves constantly in patterns both subtle and immense, twisting and turning, surging and sinking. These are the ocean's currents, invisible rivers within the sea. They shape climate, carry nutrients, scatter creatures, and complicate every attempt to explore. If pressure crushes and darkness blinds, currents confound. They transform the ocean from a static landscape into a restless wilderness. The idea of currents is familiar in small ways. Swimmers at the beach know the tug of a rip, the sideways pull that can drag you off course. Sailors for centuries depended on steady winds and predictable currents to carry them across oceans. Traders and explorers knew the Gulf Stream in the Atlantic, the Kuroshio in the Pacific, the Agulhas off Africa's coast. These great flows made global navigation possible long before engines and GPS. But what we see at the surface is only the beginning. Currents thread through the ocean at every level, some slow and subtle, others vast and roaring. Together they form a circulatory system for the planet. Part of the difficulty in understanding them is scale. Some currents are local, driven by tide squeezing through straits or wind pushing against coastlines. Others are global, stretching thousands of kilometres, transporting heat and salt across hemispheres. The Gulf Stream alone carries more water than every river on Earth combined, moving it like a conveyor belt from the tropics to the poles. These colossal flows operate constantly, day and night, regardless of weather. They are rivers without banks, defined not by land but by temperature, density, and rotation. Exploring in such an environment is like walking through a forest where the trees themselves are moving. A submersible descending straight down may find itself drifting sideways, carried kilometres off course, before it even reaches its target depth. Autonomous vehicles launched from research vessels sometimes resurface far from where they were deployed, swept away by unseen flows. Even dropping instruments on cables can become a test of patience, as currents tug and sway the line, making precise placement nearly impossible. Mapping the seafloor, photographing habitats, or collecting samples becomes more complicated than just going down. It requires fighting or cooperating with rivers that cannot be seen. Currents are also layered. Surface waters move one way, mid-depth waters another, deep waters yet another. In some regions, the directions even reverse seasonally, creating an ever-shifting puzzle. This layering is driven by differences in temperature and salinity, the thermohaline circulation that underpins the global system. Warm, salty water from the tropics travels northward, cools, sinks, and returns southward at depth. The result is a planetary conveyor belt that takes centuries to complete a single cycle. An object dropped in one place might not return to the surface until it has circled half the globe, carried silently by currents beneath awareness. For life in the ocean, these flows are both challenge and lifeline. Tiny plankton drift with them, forming the base of food chains far from where they were born. Fish migrate along currents, using them as highways. Whales follow, timing their movements to seasonal upwellings, where nutrients are brought from the depths to fuel blooms of food. Entire ecosystems depend on these invisible rivers. Without them, the ocean would stagnate. With them, it becomes a dynamic system that sustains life on a planetary scale. For humans, though, the same dynamism complicates exploration. A spacecraft can aim for Mars with precision, plotting a trajectory in a vacuum. A deep-sea probe must contend with invisible streams shifting at every depth. Predicting these flows is not trivial. Satellites can measure surface currents from space, but the deeper layers require instruments left drifting for months or years. Even then, the data are incomplete, patchy, and always changing. Oceanographers often compare the challenge to weather prediction. Just as the atmosphere swirls in chaotic patterns, the ocean churns in ways that defy easy forecasting. Currents can also be violent. Storms churn the surface into chaos, waves stacking upon swells, mixing layers that are usually separate. Tidal currents surge through narrow passages with the force of rivers, creating whirlpools and standing waves beneath the surface. Downwellings and upwellings move entire columns of water vertically, dragging nutrients or debris along with them. For explorers in submersibles or divers in suits, these motions can be disorienting, even dangerous. A shift in current can mean the difference between reaching a target site or being swept into the unknown. Then there is turbulence, the small-scale chaos that makes water unpredictable. Even in calm seas, turbulence stirs. Tiny eddies swirl, mixing heat and salt, reshaping the environment on scales too fine to map easily. For scientists, turbulence is a nightmare of complexity, yet it is also essential to life. Without it, nutrients would settle into layers and ecosystems would collapse. The very chaos that frustrates exploration is what sustains the ocean's productivity. Currents also connect surface and depth in ways that complicate our assumptions. A storm on one coast can set off ripples that affect fisheries an ocean away. Melting ice in the Arctic can alter flows that change rainfall patterns in the tropics. The sea is not isolated, it is integrated, its invisible rivers shaping climates and economies alike. When we say we cannot truly explore the ocean, part of what we mean is that it will not sit still for us. It moves constantly, weaving itself into the fabric of the planet in ways too complex for us to pin down. For those inside the ocean, this movement can be felt viscerally. Divers describe the sudden shift when a thermocline passes, a blast of cold water sliding by like a ghost. Submersibles tilt unexpectedly as they cross currents, pilots adjusting thrusters to maintain balance. Even instruments anchored to the seafloor sway in hidden surges, their readings capturing the constant restlessness. There is no stillness in the deep, no quiet bedrock except the seafloor itself. Everything else flows. From a psychological perspective, currents add to the sense of disorientation. In darkness and cold, with pressure pressing in, to also feel yourself drifting without control magnifies the unease. Up and down blur, directions lose meaning, and the certainty of position vanishes. In space, astronauts describe the clarity of stars as navigation points. In the deep, there are no stars, only currents carrying you away. It is a place where even staying put is a challenge, and yet, like pressure, darkness, and cold, currents are also part of what makes the ocean extraordinary. They knit the world together, carrying the memory of storms across basins, moving life across hemispheres, shaping the very climate that makes Earth habitable. To study them is to glimpse the hidden machinery of the planet. To experience them is to feel the sea itself alive, not static but breathing, flowing, shifting in endless rhythm. Explorers must respect this rhythm. Missions are planned around currents, timed with tides, designed with drift in mind. Some vehicles surrender to the flow entirely, drifting for years and sending back data from wherever the water takes them. These drifters give us glimpses of patterns too vast for any one ship to map. Others fight currents with powerful thrusters, burning through batteries in the attempt to hold position. Each approach is a compromise, a negotiation with the moving medium. Unlike land or space, the ocean will not yield to stillness. It insists on motion. The irony is that while currents frustrate our efforts to explore, they also connect us to the ocean every day. They carry heat that shapes our weather. They deliver fish that feed our tables. They transport pollutants and plastics across the globe. They are not only barriers, but also bridges, linking every shore to every other. When we say the ocean is unexplored, it is not just because it is dark and deep. It is because it is moving, always moving, and we are creatures who like to map fixed things. The sea resists by refusing to be fixed, and so, as we drift with this thought, we see that currents are not merely obstacles, but reminders of the ocean's identity. It is not a static place waiting to be catalogued. It is a restless system, dynamic and alive, its invisible rivers shaping both itself and us. To explore it fully would mean not only building machines strong enough to endure, but also developing patience for a world that never holds still. The ocean flows on its own terms, and our task, if we wish to understand it, is to learn how to flow with it. Of course, movement alone does not define the deep. Within this restless, shifting environment live creatures stranger than any science fiction invention, beings adapted to conditions we would find impossible. The ocean's inhabitants have evolved not just to survive, but to thrive in pressure, darkness, cold, and chaos. And it is to them we turn next, to see how life itself has written rules we barely understand in the hidden depths of the sea. If the weight of the ocean, the loss of light, the chill of its depths and the restlessness of its currents all conspire to keep us out, they also create conditions where life takes on forms almost unimaginable to us. When we picture living things, we rely on what we know: trees with branches reaching upward, birds flying through air, mammals walking on land, fish darting through sunlit shallows. But the deeper you go, the more those assumptions collapse. At depth, where pressure would crush us, where darkness blinds us, where cold slows us, and where currents toss us, life still persists. More than persists, it thrives. Yet it does so by following rules that look nothing like the ones we learned in school. In the deep sea, survival is built on strangeness. Take size, for example. In the deep, creatures push extremes in both directions. Some are giants, larger than anything their surface relatives could be. Squid stretch longer than buses. Jellyfish unfurl tentacles tens of meters long. Fish swell into grotesque shapes. The absence of sunlight and the abundance of open space make gigantism possible, and pressure itself, oddly enough, does not always limit size. At the same time, other organisms go to the opposite extreme. Tiny shrimp, fragile worms, bacteria barely bigger than viruses thrive in numbers so vast they outweigh larger animals many times over. In the deep, scale has no clear rule. It is as if life forgot to agree on a standard size and instead tried every possibility at once. Colour too follows different logic. In the shallows, fish flash bright reds, yellows, and blues, colours shaped by light and vision. In the deep, where light vanishes, many creatures are transparent, their bodies ghostly outlines drifting in blackness. Others are pigmented in ways that don't match our eyes' expectations. Some deep fish are red, a colour that disappears entirely in low light, making them effectively invisible. Others are a black so deep they reflect less than 1% of incoming light, disappearing completely in the abyss. These animals are cloaked in invisibility, shaped not for beauty but for vanishing in a place where sight itself barely works. Then there is light created by life itself. Bioluminescence is almost universal in the deep, a currency of survival that shapes behaviours in ways we can barely imagine. Some creatures glow faintly, using light as camouflage, matching the dim shimmer of the water above so predators below cannot see their silhouettes. Others flash to communicate, signalling mates or rivals. Some wield light as lure, dangling glowing appendages that attract prey directly into their waiting jaws. Still others use it as defense, ejecting bursts of glowing fluid to confuse attackers, much as a squid on the surface ejects ink. To descend into the deep is to enter a world of living lanterns, a constant play of glows and flickers where evolution has written rules we never anticipated. Perhaps the strangest adaptations are those tied to food. In the deep sea, there is no sunlight, and therefore no photosynthesis. Energy must come from elsewhere. Much of it arrives as marine snow, a gentle rain of organic debris from the surface, tiny bits of dead plankton, fecal pellets, fragments of larger animals. This snow drifts endlessly down, feeding life at every layer. For some creatures, catching enough of it is enough. They filter, graze, and wait patiently for the slow bounty. For others, the scarcity demands creativity. Some fish have jaws that unhinge to swallow prey larger than themselves, stomachs that stretch to store meals they might not see again for weeks. Others drift nearly motionless, conserving energy in ways that seem impossible to creatures like us, who must eat daily to survive. And then there are the ecosystems that bypass the surface entirely. Around hydrothermal vents, where superheated water rich in minerals gushes from the seafloor, life has found a foothold. Here, instead of sunlight, bacteria harness chemical energy, using hydrogen sulfide and other compounds as fuel. Around these microbes gather entire communities. Tube worms meters long with no mouths or stomachs, crabs with hairy claws that farm bacteria, fish and shrimp adapted to withstand temperatures swinging from near freezing to hot enough to kill most surface species. These ecosystems are completely independent of the sun. For billions of years, we assumed all life ultimately depended on sunlight. The deep proved otherwise. Other strange strategies emerge in places equally unlikely. Some fish float upside down just below the ceiling of brine pools, dense underwater lakes that form where salt concentrations are high. These pools are toxic to most life, but certain organisms exploit the boundary, skimming nutrients from the edge of what would kill them if they sank too far. Other creatures live inside the bones of whales that sink to the bottom, entire communities springing up around carcasses, feeding for decades on the last remains of giants. Life at the edge of impossibility means taking every niche, every fragment, every strange chemical trick, and turning it into survival. Reproduction too bends familiar rules. In environments where encounters are rare, strategies shift. Some species carry both male and female organs, ready to reproduce with anyone they meet. Some males fuse permanently to females, becoming little more than appendages that provide sperm on demand. The famous anglerfish does this. A tiny male latches onto a massive female, his body merging until he is little more than a set of gonads, fed by her bloodstream, existing only to fertilize her eggs. It's a strategy that would horrify us on land, but in the vast emptiness of the deep, it ensures the continuation of the species. The strangeness of these rules often leaves scientists humbled. Each expedition turns up creatures so bizarre they defy classification. Fish with tubular eyes that swivel upward through transparent skulls, jellyfish with bells glowing like neon lights, worms that secrete shimmering mucus nets to capture passing particles. Every dive seems to rewrite what we thought possible. If we'd invented life from imagination, we would not have dreamed these forms. The ocean reminds us that biology is not bound by our expectations. Exploring these creatures is not easy. Pressure destroys samples on the way up, turning delicate forms into mush before they can be studied. Cold kills organisms accustomed to near-freezing stability. Darkness means many have never been seen alive, only glimpsed on brief videos or captured in fragile nets. Scientists struggle to build containers that maintain pressure, cold and dark all the way to the lab. Even then, many species resist survival outside their native conditions. Our understanding of deep-sea life is therefore piecemeal, fragmented, glimpsed, but not fully known. The ocean keeps its secrets not only in geology and geography, but in biology itself. And yet each discovery reminds us why exploration is worth the effort. A shrimp that snaps its claw so fast it creates a bubble of heat, nearly as hot as the sun's surface. A fish with antifreeze proteins in its blood. A snail with a shell armoured in iron sulfide, harvested from vent minerals, the only known animal to incorporate metal into its body in this way. These are not just curiosities. They expand our sense of what life can be, of what biology can achieve, and of what might be possible beyond Earth. If life can exist in the frozen dark under crushing pressure and chaotic currents, then perhaps it can exist under the icy crust of Europa or in the methane lakes of Titan. The deep sea is not just an oceanic frontier, it is an astrobiological one. For humans, encountering these creatures is more than scientific, it is emotional. There is awe in seeing a giant squid's tentacle emerge from the black, or a glowing jellyfish drift past like a living chandelier. There is fear too, the reminder that we are not the only predators, that evolution has produced teeth, claws, and poisons adapted to conditions we cannot withstand. The deep sea does not revolve around us. Its rules were written without us in mind, and they remind us of our smallness. This strangeness also shapes culture. Myths of sea monsters, krakens, leviathans, all grew from glimpses of real deep-sea giants, brought up by fishermen or washed ashore after storms. Even today, headlines erupt whenever a new creature is filmed. A giant squid alive in its habitat, a shark with a face like a fossil. These stories echo because they tap into something primal. The unknown is not empty. It is filled with life that bends rules, and we are both terrified and fascinated by that fact. But with fascination comes responsibility. These ecosystems, strange as they are fragile. Deep-sea trawling scrapes centuries-old corals to rubble. Mining ventures eye the mineral-rich nodules on the seafloor, threatening habitats we have only just discovered. Pollution drifts downward, plastic fibres found even in the stomachs of trench-dwelling amphipods. The creatures that seem indestructible, surviving where nothing should, are still vulnerable to our carelessness. To explore is one thing, to protect is another. And the ocean demands both. Life at the edge of impossibility is not a sideshow, it is the main event, the majority of life on Earth existing in forms we cannot easily see. The shallow seas we swim in, the coasts we build on, the surface we sail, these are the margins. The heart of the ocean is the deep, and the rules of life there are stranger than anything we expect. To admit we cannot truly explore the ocean is to admit we cannot fully know these creatures, these ecosystems, these strategies, but each attempt brings us closer, each dive reveals more, Each strange adaptation teaches us something about biology, about resilience, and about possibility itself. And so, as we drift from this realm of creatures and their impossible rules, we turn back to ourselves. For as strange as they are, the real limit to ocean exploration is not them but us. Our bodies are fragile, our lungs delicate, our need for air relentless. If the deep is a place where life can rewrite rules, then our species is the one most bound by them. And that brings us to the next part of our journey, the limits of human bodies, and why, for all our technology and training, we remain clumsy visitors in a world not meant for us. For all the wonders we've seen in the deep, the glowing creatures, the shifting currents, the immense weight pressing from every side, there is still one truth that sits at the heart of ocean exploration. The biggest obstacle isn't the technology, though that is fragile. It isn't the unknown ecosystems, though they are strange. It isn't even the cost, though that is staggering. The greatest obstacle is us. Human bodies are built for a very narrow set of conditions, a thin band of pressure, temperature, light, and oxygen. On the surface of Earth, within that thin band, we thrive. The moment we step outside it, we are exposed as fragile travellers in a heavy world. Consider the simple fact of breathing. On land, breathing is so effortless that we forget it's happening most of the time. Lungs inflate, air rushes in, oxygen crosses into the blood, and life continues without conscious thought. At sea level, the oxygen content of the atmosphere is enough to sustain us, and our bodies are calibrated to balance it perfectly. But move into water, and the first thing taken away is that air. Breathing, the most basic rhythm of our existence, becomes impossible without assistance. Masks, tanks, regulators, all must stand in for the open air, and the deeper we go, the more complicated it becomes. Oxygen, so safe at the surface, becomes toxic under pressure. Nitrogen, harmless in every breath we take, turns narcotic. Even carbon dioxide, the waste we exhale, builds up more quickly when the body is stressed in water. Breathing underwater is not just harder, it is an elaborate juggling act of chemistry, timing, and constant vigilance. Professional divers train for this. They carry carefully mixed gases, shifting compositions as they descend, replacing nitrogen with helium, adjusting oxygen levels to remain safe. They practice decompression schedules, ascending in careful stages so dissolved gases escape the blood safely. A mistake in this choreography can mean dizziness, paralysis, or death. And these are just the rules within a few hundred meters. Beyond that, the limits of our biology shut the door entirely. Even the most skilled divers cannot pass the threshold set by chemistry and pressure. The deep ocean is simply off limits to unprotected human bodies. Temperature adds another limit. Our internal thermostat keeps us near 37 degrees Celsius, and our systems begin to fail if we drift too far from that point. In cold water, heat drains away from us 25 times faster than in air. Even with wetsuits or dry suits, survival is measured in hours at best in near-freezing depths. Hypothermia is not just about discomfort. It clouds judgment, slows reflexes, and robs the body of energy. Muscles cramp, hands lose coordination, minds drift towards sleep. For deep explorers, cold is as dangerous as pressure, gnawing away at both strength and awareness. Machines can be built to resist, but our bodies cannot. Then there is orientation. On land, gravity pulls us down, our feet find the ground, and our eyes tell us where the horizon lies. In the deep ocean, none of this works the same way. Darkness hides the horizon. Buoyancy cancels the feeling of weight. Currents tilt and twist. Divers describe vertigo, the unsettling sensation of not knowing which way is up. Some follow the trail of their bubbles to find the surface. In submersibles, pilots rely on instruments, because the water outside offers no reference points. Our senses, tuned for air and land, falter in the sea. The very act of knowing where we are becomes a struggle. The limits of human endurance go further still. The body depends on subtle balances, of pressure inside ears and sinuses, of fluid in cells, of oxygen in blood. Change those balances and systems fail. Barotrauma can rupture eardrums, crush sinuses and damage lungs. High-pressure nervous syndrome, a condition that affects divers using helium mixtures at great depth, produces tremors, confusion and nausea. Decompression sickness can cripple or kill. These are not rare accidents, but constant risks, reminders that our biology was never meant to leave the thin band of conditions at the surface. Astronauts face challenges too, but there is a difference. In space, the environment is hostile but predictable. A spacecraft can create a bubble of Earth-like conditions, sealed and stable. In the ocean, the environment presses in constantly. A submersible must not only hold air but withstand crushing pressure, shifting currents, freezing temperatures. There is no stable bubble. The ocean insists on contact, on intrusion, on reminding us that we do not belong. Our bodies betray us at every turn, fragile shells trying to survive in a medium not made for us. Psychology adds another layer. In space, astronauts speak of awe, of the overview effect, of seeing Earth in its entirety. In the deep ocean, explorers describe claustrophobia, anxiety, and the uncanny awareness of being surrounded by weight and dark. The human mind is tuned to light, air, and openness. The deep sea offers none of these. Isolation is total. Communication is limited. The awareness that failure means instant death presses in alongside the water. To sit in a small sphere kilometers below the surface is not just a test of endurance, it is a test of sanity. This fragility shapes how we explore. Most of the ocean's research is done by machines, not people. Remotely operated vehicles, autonomous drones, tethered instruments, they go where we cannot. Even when humans descend, they do so inside protective shells, separated from the environment they are supposedly exploring. We peer through windows or cameras like visitors in an aquarium. Our presence is always mediated, never direct. Unlike the creatures of the deep, whose bodies are made for it, we remain strangers wrapped in armour. And yet, despite all these limits, humans keep trying. We build better suits, stronger submersibles, more advanced life support systems. We train divers to endure longer, to descend deeper, to push the boundaries inch by inch. We refuse to accept the verdict of our biology, even as it reminds us over and over of its fragility. This determination is admirable, but it is also sobering. Each advance is expensive, risky, and temporary. Each dive into the deep is measured in hours, never days. We may extend our reach, but we cannot erase our limits. What makes this contrast striking is how well other creatures do what we cannot. Sperm whales dive to over 1,000 meters on a single breath, holding it for more than an hour. Elephant seals slip to depths of 2 kilometers routinely. Even penguins plunge into frigid waters that would paralyze us in minutes. These animals evolved for the deep in ways we can barely comprehend. Flexible rib cages that collapse safely under pressure, blood that stores vast amounts of oxygen, metabolisms that slow to conserve energy. They are reminders that the deep is not inherently unlivable. It is just unlivable for us. The irony is that we, the species capable of building rockets, computers, and satellites, are undone by something as simple as water. The ocean is not far away. It laps at our feet, covers most of our planet, sustains the climate we depend on. And yet it remains closed to us because our bodies cannot cross its thresholds unaided. We are creatures of air, fragile travellers in a heavy world, limited by lungs, skin and nerves that evolved for land. To truly explore the ocean would mean reimagining ourselves as much as our machines. Still, even in fragility there is curiosity. Divers speak of the silence, the stillness, the strange beauty of floating in another medium. Submersible pilots describe the awe of seeing glowing creatures drift past their portholes, the humbling scale of seafloor ridges and trenches. These experiences remind us why we push against our limits despite the risks. Fragile though we are, we're also restless, unwilling to accept boundaries without challenge. But our bodies set those boundaries, and so the ocean reminds us of humility. It tells us that we cannot simply conquer it with willpower. We need machines, suits, and strategies because our bodies were never meant to belong here. Exploration is always borrowed time, borrowed breath, borrowed heat. And that perhaps is what makes the ocean feel so mysterious. It is a realm not just unknown but fundamentally incompatible with us. As we carry this thought, we move from the body to the shells we build around it, from our fragile biology to the technology we use to compensate. For all the risks and limits, humans have not stopped building submarines, diving suits, and other contraptions to reach deeper. The next part of our journey belongs to these awkward attempts at belonging, the ways we wrap ourselves in armour to visit a place that never invited us, and the lessons those machines teach us about both ingenuity and vulnerability. When we admit that our bodies are too fragile for the ocean, the natural next step is to ask what we can build to make up for that fragility. For as long as people have looked at the sea, they have tried to find ways to go under it. Early attempts were little more than experiments in holding breath or carrying air in crude containers. A diver might descend with a stone to weigh them down, and a hollow reed to breathe through. Another might bring a bell-shaped contraption lowered from a ship, trapping air inside long enough for someone to linger beneath the waves. These were clumsy beginnings, dangerous and unreliable, but they carried the spark of the idea that humans could borrow time in the deep if they brought their own pocket of air. The diving bell became one of the first real tools of underwater exploration. A simple chamber, open at the bottom, it trapped air so a person could breathe inside while submerged. It allowed work on shipwrecks, salvage, and harbour construction centuries before modern technology. But it had obvious limits. The air grew stale, the pressure unbearable, and the range minimal. Still, it planted the seed of a principle that would guide centuries of engineering. If you cannot adapt your body to the ocean, bring a piece of your world down with you. From bells came suits. At first, they were little more than waterproof outfits with helmets attached, fed by pumps on the surface pushing air through hoses. The image of a diver in a heavy canvas suit, helmet round and brass-ringed, boots weighted with lead, has become iconic. These suits allowed humans to walk on the seafloor in shallow waters, repairing ships, recovering cargo, building docks. They were awkward, heavy, and tethered to the surface, but they expanded our reach. They also came with risks. A broken hose, a failed pump, or an entangled line meant drowning. The suits brought access, but always with strings attached, literally and figuratively. As technology advanced, so did the ambition. In the 20th century, inventors began to imagine suits that could withstand true depth, not just the shallows. Some built articulated shells of metal, each joint sealed with gaskets, each limb stiff but movable, the whole structure resembling a human-shaped submarine. These atmospheric diving suits, as they came to be called, looked like something from science fiction, bulky, metallic, and strange. Inside, a diver could remain at surface pressure while descending hundreds of meters. No need for decompression, no risk of nitrogen narcosis, but there were trade-offs. The suits were heavy, expensive, and limited in mobility. Every motion was effortful. Working in them felt like trying to perform surgery while wearing a suit of armour. While suits tried to keep the human body inside its comfort zone, submarines and submersibles took a different approach. Rather than wrapping the diver in a shell shaped like a person, they placed people inside spheres or cylinders and carried them down as passengers. These machines varied in size, from military submarines designed for stealth and warfare to tiny research craft, barely large enough for one person. The underlying principle, however, was the same: enclose humans in a bubble of air, reinforce it against pressure, and provide controls to move. The first submarines were crude, built centuries ago with hand-cranked propellers and leaky hulls. They were more curiosities than practical tools, often sinking themselves before achieving anything meaningful. But each failure taught lessons, and by the 20th century, submarines had become not just reliable but strategic. During World Wars, they proved their power in combat. Afterward, they proved their potential in exploration. Nations began sending submarines to explore shipwrecks, trenches, and seafloor features, gathering knowledge impossible to gain from the surface. Research submersibles marked another leap. Unlike military submarines, which emphasized range and stealth, these were designed to go down. The bathyscaphe Trieste, for example, descended in 1960 into the Mariana Trench with 2 men inside, reaching nearly 11 kilometers deep. They sat in a tiny steel sphere, suspended beneath a larger float filled with gasoline to provide buoyancy. The descent took hours, and the experience was cramped, dark, and unnerving, but it proved that humans could reach the very bottom of the sea. For decades afterward, only a handful of similar dives occurred. The cost, risk, and engineering challenges meant such missions were rare and symbolic more than practical. In more recent years, advances in materials and design have produced sleeker submersibles. Filmmaker James Cameron built one to dive solo into the Mariana Trench, emphasizing not just depth, but maneuverability, allowing him to film and sample along the way. Private companies have developed tourist subs for shallow dives, luxury vehicles for those wealthy enough to purchase them. Yet even at their most advanced, these machines remain awkward. They are slow, limited in range, dependent on surface support ships, and always balanced precariously against the immense pressure outside. The awkwardness of our attempts shows in scale. Spacecraft are large enough to carry laboratories, dormitories, even gyms. Submersibles are barely large enough to fit their crew. The reason is simple. The deeper you go, the stronger the hull must be, and strength increases with thickness. A larger craft would need impossibly thick walls. The result is that most deep-diving subs are cramped spheres, just wide enough for people to sit shoulder to shoulder among blinking instruments. Claustrophobia is part of the package. Comfort is not a priority. Safety and function always come first. The suits and subs we've built are remarkable, but they reveal our limits more than they erase them. Each one is a compromise, trading mobility for safety, visibility for strength, or endurance for power. Divers in suits cannot move with the grace of fish. Pilots in submersibles cannot roam as freely as whales. Our machines are clumsy imitations of adaptation, placeholders that allow brief visits but never belonging. They give us glimpses, not residence. And yet, awkward though they are, these machines have shown us wonders. Through portholes and cameras, we have seen shipwrecks frozen in time, hydrothermal vents spewing minerals into the dark, and creatures glowing with alien beauty. Submarines have mapped trenches, studied undersea volcanoes, and even recovered artifacts from centuries past. Each dive adds to our understanding, but always within the narrow window the machines permit. Hours, not days. Kilometers, not oceans. Our attempts at belonging remain temporary. There is something almost poetic about this awkwardness. We, a species that has walked on the moon, still squeeze ourselves into tiny spheres to visit our own planet's depths. We dream of colonizing Mars, yet cannot build a permanent habitat on the seafloor. Our submarines are like borrowed shoes, letting us step into a world we do not fit. Our suits are like costumes, disguises that trick the ocean into tolerating us for a short while. We pretend at belonging, but the ocean always reminds us that we are out of place. The question is whether this awkwardness will always remain. Engineers imagine future subs built of new materials, lighter yet stronger. Suits with robotics to amplify movement, allowing divers to work more naturally. Habitats that might one day rest on the sea floor, pressurized and supplied to house humans for longer periods. Some of these ideas have been tested in prototypes, like underwater laboratories where scientists live for weeks at a time, but these remain exceptions, experiments rather than norms. For most exploration, we still rely on remote vehicles because they are cheaper, safer, and less awkward than putting humans inside pressure-resistant shells. The ocean doesn't make it easy. In space you can scale up. Larger rockets, larger stations, larger vehicles. In the deep, scaling up makes everything harder. Pressure grows, strength requirements multiply, costs balloon. That is why submarines and suits remain small, awkward, and limited. They reflect not just where our technology is, but what the ocean demands. Still, awkwardness does not mean failure. Each dive, each mission, each attempt expands the boundary of what is known. We may not belong, but we visit. We may not live in the deep, but we witness it. The awkward tools we build are extensions of ourselves, fragile yet determined, clumsy yet curious. They remind us that belonging is not always necessary for exploration. Sometimes, a glimpse is enough to change how we see the world, and those glimpses matter. A diver in a suit repairing a ship, a submersible pilot gazing at a glowing jellyfish, a team recovering samples from a vent, all are part of the story of how humans stretch against limits. We may never be graceful in the ocean, but we continue to try. Awkward attempts at belonging may not grant us permanence, but they grant us knowledge, and knowledge is what keeps us building, diving, and dreaming. But knowledge comes at a price. Submarines, suits, and support ships are costly, their missions demanding enormous resources. Every hour in the deep represents years of preparation, millions of dollars, and the risk of failure. And that brings us to the next barrier, one less physical but no less real. The sheer cost of curiosity, the economics of exploration, and how money shapes where and how often we dare to descend. Curiosity has always come with a price. Every great expedition in history required resources, whether it was ships to cross unknown seas, caravans to traverse deserts, or rockets to leave the atmosphere. But when it comes to the deep ocean, that price multiplies in ways that are hard to imagine. It is not just about money in the abstract. It is about the sheer effort of building machines that can survive where we cannot. The logistics of supporting missions far from shore, the training, the risks, the fuel, the design, and the fact that every small mistake carries catastrophic consequences. The ocean is expensive not because we are careless, but because every law of physics conspires to make it so. Think about the starting point. Building a vessel that can withstand pressure. Every millimetre of hull thickness, every weld, every joint must be perfect. A spacecraft must be strong too, but once it leaves Earth's atmosphere, it operates in a vacuum where pressure is absent. A submersible, by contrast, faces the relentless squeeze of tons of water from every direction. To resist that squeeze means using rare materials, custom engineering, exhaustive testing. There is no shortcut, no cheap version that still works. A single flaw means failure, and failure in the deep is not just an inconvenience. It means losing the entire vehicle, sometimes with people inside. That risk pushes cost upward. Then consider the support needed. A deep-sea mission cannot begin from the shore. It requires a ship, usually a larger research vessel, capable of carrying the submersible or remotely operated vehicle, along with crew, scientists, engineers, and supplies. These ships cost tens of thousands of dollars per day to operate, sometimes far more. Fuel alone for a voyage across oceans can be staggering. Crew salaries, equipment maintenance, food, and logistics add up quickly. Unlike a laboratory on land, which can run continuously once built, each ocean mission is a self-contained expedition, with a clock ticking from the moment the ship leaves port. The dives themselves add another layer. Each descent consumes not only power and fuel, but also precious time. Batteries must be charged, systems checked, weather conditions monitored. Launching and recovering a submersible is a delicate operation requiring cranes, winches, and skilled coordination. A dive might last only a few hours, but it takes days of preparation and recovery. That ratio of effort to outcome makes every hour in the deep extraordinarily costly. When scientists say that we know more about Mars than our own seafloor, part of the reason is that satellites can map Mars cheaply from afar, while the ocean demands expensive, painstaking effort for each tiny piece of information. Technology itself is not reusable in the same way as space instruments. Rovers on Mars last year's operating on solar power, sending back gigabytes of data continuously. Submersibles often require extensive maintenance after each dive. Saltwater corrodes, pressure stresses parts, and recovery can damage delicate instruments. Every mission has a built-in expectation of repair and replacement. Budgets must account not only for building machines, but for rebuilding them over and over. Insurance and safety add their own burdens. Sending people into the deep involves risks so high that precautions must be layered thick. Every system must have redundancies. Emergency plans must be rehearsed. Even then, accidents happen, and when they do, the costs, both financial and human, are immense. After each failure, regulations tighten, designs are re-evaluated, and costs rise further. Exploration becomes not just a matter of building machines, but of building trust, convincing funders, governments, and crews that the risks are worth taking. There is also the cost of invisibility. Space exploration captures public imagination easily, because telescopes produce images, galaxies, planets, nebulae, stunning pictures that justify budgets. The ocean rarely offers such spectacle. Photographs from the deep are often murky, grainy, or bewildering to the untrained eye. To the scientist, a fuzzy image of a worm or shrimp is thrilling, but to the public it looks unimpressive compared to the rings of Saturn or the surface of Mars. That lack of visual drama means funding is harder to secure, and each project must fight for attention against more glamorous endeavours. The ocean is no less mysterious, but it is harder to sell. Private ventures face similar challenges. A wealthy individual might fund a deep-sea dive, as some have done, but even billionaires cannot easily absorb the recurring costs of regular exploration. Building one submersible for a record-breaking descent is feasible. Maintaining a fleet, funding crews, supporting long-term science, those require institutions, governments, or global cooperation. This is why only a handful of organisations around the world have consistent access to the deep. It is not a lack of curiosity. It is the economics of maintaining fragile, expensive equipment in a hostile environment. Compare this with space once again. Space agencies can share rockets, satellites, and infrastructure. A launch site can serve multiple missions over decades. A telescope in orbit continues to collect data long after its cost is paid. The ocean does not grant such efficiency. Each dive is temporary, each mission a reset. Even autonomous vehicles that drift for years must eventually be retrieved, maintained, or replaced. Nothing is permanent in saltwater. Rust, biofouling, and pressure guarantee decay. This cycle of replacement drives costs upward endlessly. The cost also limits scale. Oceanographers often say that if they had the budget of a single Mars rover, they could map vast sections of the seafloor in detail. Instead, they make do with small grants, short voyages, and patchwork surveys. The result is a paradox. We spend billions to explore other planets while leaving most of our own planet unmapped and unstudied. Not because we don't care, but because each kilometre of ocean requires more resources than a comparable kilometre in space. There are hidden costs as well, the ones not often discussed. Training personnel takes years. Maintaining expertise requires continuous funding. If a program is cut, the knowledge can dissipate quickly, and rebuilding it later is even more expensive. Exploration is not just about machines. It is about people who know how to design, pilot, repair, and interpret. Without steady investment, those skills vanish, and with them the ability to explore. This fragility of human infrastructure mirrors the fragility of our machines. Both require constant care. And then there is politics, Funding agencies weigh costs against perceived benefits. Ocean exploration promises scientific knowledge, but not always immediate economic or strategic return. Governments are more easily persuaded to invest in fisheries, shipping lanes, or military submarines than in pure science dives to trenches. The result is uneven support. Some areas of the ocean are studied heavily because they matter economically. Others, equally mysterious, remain untouched because they are harder to justify in a budget. Cost in this sense does not just slow exploration, it shapes its geography. But cost is not only a burden, it also reflects the true difficulty of what we are attempting. To build machines that survive where human bodies collapse, to sustain research in places never meant for us, to retrieve knowledge from an environment that resists at every turn, these are inherently expensive goals. The ocean is reminding us through its costs that exploration is not a casual activity. It is an extraordinary effort, requiring extraordinary commitment. That commitment comes at a price measured in money, time, and risk. Still, there is irony here. For all its expense, the ocean is central to our survival. It regulates climate, produces oxygen, provides food, and supports economies. We depend on it daily, yet we hesitate to invest in understanding it. The true cost may not be the money spent, but the money not spent. The price we will pay for ignorance in the face of rising seas, collapse in fisheries, and changing currents. Exploration is not just curiosity, it is preparation. To neglect it because it is expensive is to risk costs far greater later. And so the barrier of cost remains, as invisible and relentless as pressure, darkness, or cold. It determines how often we dive, how far we go, and what we learn. It explains why entire mountain ranges beneath the sea remain unmapped, why ecosystems vanish before we ever see them, why myths persist about monsters in the deep. It is not that we lack curiosity, it is that curiosity demands resources, and resources are scarce. The ocean is vast, hostile, and expensive, and those three words keep it unexplored. But cost, though heavy, is not the only subtle barrier. Even when money is secured, machines are built, and missions launched, the ocean introduces another complication. The way sound and silence work differently underwater. Communication falters, navigation becomes strange, and the very physics of the medium force us to rethink how we sense and explore. Having counted the cost, we must now listen to the sea and discover how sound itself reshapes the experience of diving into its depths. When we think of silence, we usually imagine the absence of sound. A quiet room, a library, a moment in nature when the wind pauses and birds stop singing. Silence feels empty, peaceful, sometimes unsettling. But in the ocean, silence means something different. Beneath the surface, sound behaves in ways that defy our instincts. It travels faster, farther, and with strange distortions, so that the deep is never truly silent and never truly predictable. For explorers, this is both a gift and a barrier. A way to sense the unseen, but also a reminder that the rules of hearing on land do not apply underwater. The first thing to understand is speed. In air, sound travels at about 340 meters per second. In water, it travels more than 4 times faster, around 1500 meters per second, depending on temperature, salinity, and pressure. That difference changes everything. On land, we instinctively use the time delay of sound to locate direction. We hear a bird call to the left because the sound reaches one ear slightly sooner than the other. Underwater, the delay is almost non-existent. Sound arrives at both ears nearly simultaneously, and our brains, built for air, struggle to interpret direction. For divers, this means disorientation. A noise may seem to come from everywhere at once, a confusion that adds to the alien feel of being submerged. Distance adds another twist. In air, sound fades quickly, shouts vanish within hundreds of meters. In water, sound can travel for hundreds, even thousands of kilometers. The low-frequency calls of blue whales, the largest animals on Earth can cross entire ocean basins. Naval sonar pings echo across seas. For submarines, this is both tool and threat. Sonar allows detection, but it also reveals presence. The ocean is a soundscape stretching beyond imagination, filled with signals both natural and artificial, overlapping and echoing endlessly. Explorers rely on this property because light cannot penetrate far. Cameras show only what is near. Sonar, by contrast, can map entire regions. A simple echo sounder on a ship sends pings downward, measuring the time until echoes return, drawing outlines of the seafloor. More advanced systems sweep side to side, building images of underwater landscapes. Multi-beam sonar creates detailed maps, revealing ridges, trenches, and wrecks. These tools are invaluable, but they also show the limitations of sound. The pictures sonar produces are not photographs but interpretations, shapes built from echoes. They require training to read, and they never carry the clarity of sight. At the same time, sound's reach introduces challenges. Because it travels so far, noise in one place can disrupt life in another. Whales and dolphins depend on sound not only for communication, but for navigation and hunting. They echolocate, bouncing clicks off prey to build sonic pictures of their world. Ships, submarines, and industrial activity add layers of noise that interfere, masking signals, confusing animals, even causing strandings. The deep ocean, once imagined as a place of silence, is increasingly a place of human-made sound. Exploration does not just depend on noise, it creates it, and that noise has consequences. For humans inside submersibles, the soundscape is strange and often unsettling. The ocean creaks and groans, hulls ping as they adjust to pressure, thrusters hum, and sometimes faint biological noises filter in. Shrimp crackle in reefs, fish croak or grunt, whales moan in the distance. To sit in the deep is to be immersed in a constant symphony of sounds, many of which are difficult to identify. Unlike light, which gives clear outlines, sound blurs and blends, leaving explorers unsure what they are hearing. Some describe it as eerie, others as fascinating, but all agree it feels unlike silence on land. It is a different kind of silence, one filled with hidden vibrations. Communication adds another problem. On land or in space, radio waves allow instant transmission. In the ocean, radio fades quickly, absorbed by water within meters. Instead, explorers must use sound to send messages. Acoustic modems transmit pings, encoding data in slow, choppy bursts. A submersible sending information to the surface may do so at the speed of an old dial-up modem with delays, distortions, and dropped signals. Real-time video is impossible. Even voice communication underwater is limited to divers within short range using special equipment. The ocean cuts connections, isolating those below. In this way, the very medium that carries sound so far also muffles our ability to use it effectively. This isolation shapes exploration. When a rover explores Mars, scientists can send commands and receive images, albeit with a delay of minutes. When a submersible dives into the deep, once the hatch is sealed and the descent begins, contact becomes patchy. Pilots rely on their own judgment, their own instruments, knowing that the surface may not hear them clearly or at all. This separation increases risk and cost, but it also reinforces the feeling of being in another world. The sound of silence in the deep is not the absence of noise, but the absence of reliable communication. Sound also reveals mysteries. Scientists have recorded unexplained noises in the ocean, some later identified, others still uncertain. The bloop, a powerful low-frequency sound recorded in the 1990s, was once thought to be from a giant unknown creature, but later attributed to ice quakes, massive shifts of glaciers. Other sounds remain harder to explain, echoes and rumbles that hint at geological activity, storms, or perhaps life we do not yet understand. These mysteries remind us that the ocean is not only unexplored in geography, but in acoustics. We are still mapping its soundscape, learning what belongs to biology, what belongs to geology, and what belongs to us. For animals, sound is survival. For humans, sound is obstacle and opportunity. We cannot rely on our ears and water the way whales do. We build instruments instead, clumsy imitations of natural sonar. We listen, but imperfectly. And in listening, we also disturb. Our exploration becomes part of the noise, changing the very soundscape we're trying to study. Silence in the ocean is never pure. It is always layered, always relative, always fragile. Perhaps the most striking contrast is between perception and reality. On the surface, the ocean looks peaceful. Stand on a quiet beach, and you hear only the wash of waves. Beneath, however, lies a world humming with clicks, calls and echoes, a constant communication network stretching farther than the rest we have built on land. For the creatures that live there, this is normal. For us, it is alien. Our ears are tuned to air, not water. We are strangers in an acoustic world. Explorers often describe a peculiar sensation when they turn off their lights, shut down thrusters, and drift quietly in the deep. At first, it feels like silence. Then the sounds emerge. Faint clicks, distant rumbles, the groan of water moving, the crackle of life invisible in the dark. It is a reminder that the ocean is never still. Its silence is full of meaning, if only we had the senses to interpret it properly. For us, though, the difficulty of sound underwater remains one more reason why exploration is so hard. We cannot see far, and we cannot communicate easily. We map with echoes instead of eyes. We navigate with instruments instead of instincts, and we struggle to maintain connection in a medium that warps every signal. This is not just inconvenience, it is another barrier as real as pressure and darkness, slowing every attempt to know the deep. And yet, despite these challenges, we continue. We build better sonar, more sensitive hydrophones, more robust acoustic systems. We record whale songs, trace the routes of submarines, and listen for earthquakes beneath the seafloor. Each improvement gives us clearer glimpses, but always through the filter of sound's peculiar rules underwater. The ocean insists that we adapt to its language, not the other way around. As we drift with this thought, we find ourselves circling back to one of the most humbling facts of all. For all our technology, we still know the surface of Mars better than the seafloor of our own planet. Sound carries farther underwater than light, but it still leaves us blind in many ways, and so the next step in our journey takes us into this paradox. How, with satellites orbiting other worlds and rovers crossing alien landscapes, we still cannot claim to know the mountains, valleys and plains beneath our own seas. When you look at a map of Earth, the oceans are blue. They take up most of the space, dominating the globe, covering nearly 3/4 of its surface. That blue seems simple, almost empty, as though the sea is flat and featureless, a watery expanse hiding nothing more than depth. But that image is a lie of convenience. Beneath the waves, the Earth is as dramatic as any landscape above, filled with mountain ranges taller than the Rockies, canyons deeper than the Grand Canyon, plains stretching wider than continents. The problem is that we don't see it. We still don't really know it. And that's why, despite living here, we can honestly say we understand Mars better than we understand our own seafloor. At first, that sounds absurd. Mars lies millions of kilometers away, a barren world we've never walked freely upon. The ocean lies just meters away, touching every shore, something we sail across, fish in and swim through daily. How can the distant planet be better mapped than the ground beneath our own waves? The answer lies in how information is gathered and in the simple fact that water hides. Mars, as alien as it is open to view. Orbiting spacecraft circle it constantly, photographing every canyon, every dune, every volcanic peak. Light travels freely across its surface, unimpeded by atmosphere or clouds, allowing cameras to capture details as small as a metre across. The data is stitched together into maps of astonishing precision. We can trace the meanders of dried riverbeds, the outlines of ancient craters, the layering of cliffs. Anyone with an internet connection can look up images of Martian landscapes with more detail than we have for most of our own seabed. That is the paradox. Distance is not the obstacle. Opacity is. Water is opaque to the instruments that map other planets. Satellites cannot see through it. Radar, so useful for peering beneath the clouds of Venus or the sands of the Sahara, scatters quickly in liquid. Light, of course, vanishes within a few hundred meters. From orbit, the ocean is a blue blur, its surface visible but its depths hidden. We can measure its height, track its waves, watch its currents swirl, but the floor beneath remains concealed. To map the seafloor, we must go there. And that is where the barriers of pressure, darkness, cold, and cost all collide. Ships equipped with sonar can scan the bottom, but their beams spread with depth and precision decreases. Even advanced multi-beam sonar systems which sweep wide arcs of seafloor take time. A single ship might spend years covering a small fraction of the ocean. To map the entire seabed in detail would require centuries at current rates. Instead, we have partial maps stitched together from scattered surveys, filled with guesswork in between. Global maps of the ocean floor exist, but their resolution is coarse. Features smaller than several kilometers across blur into invisibility. By comparison, the surface of Mars is mapped at resolutions of meters. We could spot a car-sized object on Mars more easily than a shipwreck in the mid-Atlantic. This lack of detail is not just academic, it has consequences. Submarine cables, vital for internet and communication, are laid across terrain we often don't fully know. Earthquakes trigger undersea landslides we failed to anticipate because the terrain was unmapped. Planes that crash into the ocean, like Malaysia Airlines Flight 370, vanish into seafloor landscapes so poorly charted that searchers become desperate hunts in darkness. Without precise maps, navigation, safety, and science all suffer. Yet the effort to improve them is slow, expensive, and often overlooked. The irony is that glimpses of the seabed we do have show extraordinary diversity. Mid-ocean ridges run like scars across the globe, splitting tectonic plates apart. Volcanic seamounts rise in chains, some rivaling Everest in height, yet hidden completely beneath water. Trenches cut so deep they could swallow entire mountain ranges. Hydrothermal vent fields bubble with strange chemistry. Ancient river channels lie buried beneath sediment. The seabed is not an empty plain. It is Earth's last great wilderness, but one that remains only sketchily drawn. Part of the reason for this neglect is visibility. Politicians, funders, and the public respond more eagerly to images of other worlds than to sonar maps of ridges and trenches. A canyon on Mars excites imagination, while a trench in the Pacific remains abstract. Pictures move people, sonar data does not. The result is that resources often flow to space agencies, while oceanography fights for scraps. This is not because one is more important than the other, but because one shows its wonders more clearly. The ocean hides, and hidden things are harder to love from afar. Technology is improving, but slowly. Autonomous vehicles now roam sections of the ocean, carrying high-resolution sonar to map with greater precision. Initiatives like Seabed 2030 aim to chart the entire ocean floor within this century, combining data from ships, subs, and satellites that infer depth indirectly through gravity measurements. These efforts are monumental, but they face the same barriers: cost, time, and the sheer vastness of the sea. Every step forward reveals how much remains unknown. And so, we live with this strange imbalance. We can watch dust devils sweep across Mars in crisp detail, but we cannot yet say with confidence what lies at the bottom of the South Pacific. We can trace the tracks of rovers across alien planes, but we struggle to follow the contours of ridges that stretch for thousands of kilometres beneath the Atlantic. We know the history of Martian volcanoes better than many of the volcanic systems beneath our own seas. The ocean keeps itself hidden, and in doing so, it keeps us ignorant of our own planet. This ignorance matters because the seafloor is not static. It is active, shaping earthquakes, tsunamis, volcanic eruptions, and even climate. Subduction zones, where one tectonic plate slides beneath another, lie beneath oceans. These are the sites of the world's largest earthquakes, disasters that ripple into human lives across continents. Without detailed maps, our ability to predict and prepare is limited. The price of not knowing is not just curiosity left unsatisfied, it is vulnerability. Explorers feel this keenly. Each dive into the deep reveals landscapes no human has ever seen, even in places close to major coasts. A mountain taller than any in Europe was discovered in the 1990s beneath the Pacific, simply because no one had mapped that patch of seafloor before. Imagine discovering a mountain range on Earth today. That is the scale of what remains hidden beneath the waves. Our planet is not fully known, not fully charted. Blue space on maps hides entire continents of geology and biology we have yet to explore. Why does this gap persist? In part because the ocean resists the tools we prefer. We are creatures of sight, and we like to see clearly. The ocean forces us to hear instead, to interpret echoes, to accept fuzziness. In space, clarity is possible. In the sea, ambiguity is built into the medium. We resist that ambiguity, and in resisting it, we turn our attention to places where certainty is easier. Mars offers clarity. The ocean offers mystery. And mystery, paradoxically, discourages funding as much as it inspires it. Yet for all these obstacles, mapping the unknown is not hopeless. Each year, new expeditions fill in blanks. Each sonar sweep reveals details once hidden. Collaborative projects pool data from navies, research institutes and private vessels, slowly improving resolution. The picture sharpens piece by piece, like a puzzle assembled in fragments. Someday, perhaps, the entire ocean floor will be mapped as clearly as any continent. But until then, the paradox remains. We know distant worlds better than the one beneath our feet. This paradox also shapes how we think of exploration itself. If knowledge is a kind of map, then ignorance is uncharted territory. The ocean reminds us that our ignorance is vast. It humbles us, reminding us that exploration is not a finished story but an ongoing one. To know the seafloor is not only to satisfy curiosity, it is to complete our picture of Earth, to understand the foundation of the planet we live on. Until then, every map we draw is a placeholder, a sketch over a mystery. And so, we drift from the thought of maps to the tools themselves. For all our advances, the machines we use still fall short. Our sensors are limited, our vehicles fragile, our data incomplete. Even with funding and willpower, technology struggles to keep up with the ocean's demands. To understand why exploration remains partial, we must look at the gap between our tools and the challenges they face, the technology we dream of versus the technology we actually have. When people imagine exploration, they often picture technology at the centre of it. The spacesuit, the rover, the telescope, the rocket. Tools are what make the impossible possible. They allow us to stretch beyond our biology and peek into realms that would otherwise remain closed. But when it comes to the ocean, the story is different. The tools we have, remarkable as they are, remain behind the curve. They give us glimpses, they give us fragments, but they cannot yet give us mastery. The ocean demands more than we are currently able to build, and that mismatch between the scale of the challenge and the capacity of our machines is what we might call the technology gap. The problem begins with pressure. A tool that works flawlessly in a lab may fail utterly at depth. Electronics short out, casings implode, seals weaken. Every instrument that goes into the sea must be redesigned for an environment that crushes relentlessly. Imagine building a delicate clock and then asking it to keep perfect time while being squeezed by thousands of tons of force from every direction. That is the engineering puzzle of the ocean. Even when we succeed, success often comes at the cost of fragility. Instruments that survive one dive may need complete overhauls before the next. Robustness is rare, and rarity means expense. Energy is another constraint. In space, solar panels spread wide, collecting light and feeding instruments for years. In the deep sea, there is no light to harvest. Vehicles must rely on batteries, which limit duration and range. A submersible may dive for only a few hours before power dwindles. Autonomous vehicles can last longer, but only by moving slowly and sacrificing capabilities. The dream of machines roaming freely for months, scanning and recording without interruption, is still largely out of reach. Every dive is a race against the clock, with precious little margin for error. Communication compounds the challenge. On land or in orbit, data streams back continuously. Satellites transmit images, rovers send videos, probes broadcast telemetry. In the ocean, water blocks most of these signals. Acoustic modems, as we've seen, are slow and unreliable. Fiber optic cables can tether remotely operated vehicles to ships, providing control and video feeds, but those cables limit range and mobility. Cut the tether, and autonomy becomes the only option, but autonomy means the machine must make decisions on its own, with no chance for mid-course correction if something goes wrong. Our tools, therefore, are caught between dependence and isolation, neither choice ideal. Durability against corrosion is another endless battle. Saltwater is one of the most corrosive environments on Earth. Metals rust quickly, plastics degrade, seals weaken. Every piece of equipment requires careful materials science, constant maintenance, and eventual replacement. Unlike a telescope in orbit, which may function for decades with minimal upkeep, ocean instruments live short, punishing lives. They are consumed by the very medium they study. This churn keeps costs high and progress slow. The technology gap is also a matter of scale. The ocean is vast beyond reckoning, and our tools are small. A single ship, even working tirelessly, can cover only a fraction of the seafloor in its lifetime. A handful of autonomous vehicles cannot map or sample the entirety of an ocean basin. The scale of the challenge dwarfs the scale of our machines. It is like trying to understand a forest by examining a few trees, or trying to map a continent with a single car. We make progress, but progress remains uneven, patchy, and partial. Even the tools we consider advanced are often blunt instruments compared to what we need. Sonar maps the seafloor, but with limited resolution. Cameras capture images, but only in narrow cones of artificial light. Sampling devices scoop up sediment or water, but disturb the environment in the process. We yearn for precision, the ability to see the deep as clearly as we see our own backyards, but our tools refuse to give it. Instead, they give us approximations, outlines, hints of what lies below. The deep stays veiled not because we don't try, but because our instruments cannot pierce fully. This gap is not just about what the ocean resists, but about what humans prioritize. Space exploration inspires massive investments, and technologies develop rapidly as a result. The ocean, by contrast, receives a fraction of that attention. Funding limits innovation. Many oceanographic tools in use today are decades old in concept, refined incrementally, but not revolutionized. Researchers often describe their field as under-equipped, forced to innovate on small budgets, reusing and adapting older devices. Ambitious ideas, swarms of coordinated autonomous vehicles, pressure-resistant long-term habitats, fleets of robotic mappers remain mostly on paper. The technology gap is not just technical, it is political and economic too. And yet, progress does happen, though often quietly. Pressure housings built of new ceramics or composites hold instruments deeper than before. Lithium batteries extend endurance, Machine learning algorithms allow autonomous vehicles to adapt better to changing currents. Cameras improve in sensitivity, capturing clearer images in low light. Each innovation chips away at the gap, but the ocean is relentless, and each step forward reveals just how much further we have to go. The difficulty is not only in making tools survive, but in making them useful. Collecting data is one thing, interpreting it is another. The ocean produces overwhelming amounts of information: sound recordings, sonar returns, chemical measurements, genetic samples. Managing and analysing this torrent requires computing power and collaboration across nations. Our ability to collect data often outpaces our ability to make sense of it. The technology gap, then, is not just in machines, but in knowledge. We can gather glimpses of the deep faster than we can integrate them into understanding. Explorers sometimes describe the feeling of futility that comes with this. A single expedition may yield terabytes of data and thousands of samples, but only a small portion will be studied before the next mission. The backlog of unanswered questions grows while the tools to address them lag behind. The ocean always stays one step ahead, larger, stranger, and more complex than our capacity to capture it. This gap has consequences beyond science. It shapes security, commerce, and environment. Submarine detection relies on sonar systems that are imperfect. Resource management relies on seafloor maps that are incomplete. Conservation relies on biological data that is fragmentary. The technology gap means we operate with uncertainty in matters that affect economies, politics, and survival. It is not simply a scientific inconvenience, it is a practical vulnerability. But there is another dimension to this gap, one less discussed but equally important: imagination. We tend to design tools that reflect our expectations. We build subs that look like spheres, suits that mimic our bodies, sonars that imitate eyes. Yet the ocean does not conform to those expectations. Its rules are different, its environment's alien. Perhaps the real gap is between our imagination and the ocean's reality. To close it, we may need to think less about forcing our tools to behave like us, and more about designing them to behave like the creatures that already thrive there. Fish glide effortlessly. Whales navigate through sound. Squid use jet propulsion. If we could mimic such adaptations in machines, perhaps we could close the distance between what we want and what the ocean demands. This is the frontier of biomimicry, building tools inspired by biology. Engineers have begun experimenting with robotic fish that swim with fins instead of propellers, drones that adjust buoyancy like jellyfish, sensors that drift like plankton. These approaches are still in their infancy, but they hint at a way to bridge the gap, not by overpowering the ocean but by learning from it. Technology may never erase the barriers entirely, but it may adapt to them more gracefully, reducing the awkwardness of our attempts at belonging. Even so, the ocean will remain ahead of us. Each improvement in tools reveals more mysteries. A new camera shows creatures we never knew existed. A new sensor detects chemicals we never knew were present. A new mapping system uncovers landscapes we never guessed were there. The technology gap is not a chasm to be crossed once and for all. It is a moving frontier, always retreating as we advance. That is part of the allure. The ocean resists being finished, and so, as we reflect on this gap, we find ourselves drawn to the hidden landscapes that wait beyond our current reach. For every trench we have visited, dozens remain untouched. For every volcano we have surveyed, hundreds lie unmapped. For every vent we have studied, entire fields may exist unseen. The technology we have keeps us chasing the horizon, never quite catching up. But in that chase lies discovery, and discovery is what drives us forward. From here, the story bends naturally toward those hidden features, the volcanoes, the trenches, the architecture of the planet itself that lies beneath the waves. If technology lags, those landscapes remain mysteries. To understand them is to understand not only the ocean, but the Earth itself, and so we turn next to the seafloor's secret architecture, the unseen structures that shape both the planet and our experience of it. Beneath the surface of the sea, hidden under kilometres of water, the Earth is sculpted in ways more dramatic than almost anything on land. We live on continents and islands, we see mountains and valleys, we drive across plains and deserts, and we assume this is the full range of our planet's shapes. But the true architecture of Earth lies not on the land we inhabit, but on the seafloor we rarely glimpse. There, in the darkness and pressure, are features that dwarf anything above sea level. Volcanoes taller than Everest, canyons deeper than the Grand Canyon, mountain ranges longer than the Andes, and plains wider than any desert. The irony is that these are not exotic oddities. They are the majority of Earth's surface, and yet most of us will never see them, because they are hidden beneath water. The most prominent structures are the mid-ocean ridges. Stretching for more than 60,000 kilometres, they form a continuous mountain chain encircling the globe. If lifted above sea level, they would be the longest mountain range on Earth, winding through every ocean basin. These ridges are where tectonic plates diverge, where magma rises to create new seafloor. They are factories of rock, constantly adding to the planet's crust, reshaping the ocean floor in slow but relentless ways. The ridges are not just lines on a map. They are dynamic landscapes, with peaks, valleys, and volcanic vents. Some rise high enough to break the surface as islands. Iceland, for example, is part of this system. But most of it remains hidden, a colossal backbone of Earth we know mainly through sonar scans and scattered dives. Equally dramatic are the trenches, the deep scars where plates converge. The Mariana Trench in the Western Pacific is the most famous, plunging nearly 11 kilometres deep. But it is not alone. The Tonga Trench, the Philippine Trench, the Peru-Chile Trench all carve into the seafloor with depths that stagger the imagination. These trenches mark places where one tectonic plate is forced beneath another, descending into the mantle. They are sites of earthquakes, tsunamis, and immense geological power. Standing at their edges would be like looking down cliffs so vast that scale itself breaks. Yet no human eye has seen most of these places directly. Our knowledge comes from instruments, from echoes returning through water, from brief descents in fragile spheres. The architecture of the planet is there, immense and active, but out of sight. Between ridges and trenches lie volcanic arcs, seamount chains, and abyssal plains. Volcanic arcs form where descending plates melt, feeding magma that rises to create lines of volcanoes. Some emerge as islands, the Aleutians, the Japanese archipelago, the Lesser Antilles. Others remain submerged, mountains taller than any terrestrial peak but flattened by waves long ago. These seamounts dot the ocean floor by the tens of thousands, each an undersea volcano, many extinct, some still active. They rise abruptly from abyssal plains, isolated giants in a desert of depth. Their slopes host unique ecosystems, their tops sometimes eroded into flat-topped plateaus called guyos. Despite their abundance, only a small fraction have been mapped or studied. Some scientists estimate that more than 100,000 seamounts over a kilometre tall exist, hidden from sight, shaping currents, habitats, and biodiversity in ways we barely understand. The abyssal plains themselves are no less impressive, though their drama is in scale rather than height. These plains stretch for thousands of kilometres, flat expanses of sediment that cover much of the sea floor. They are some of the flattest surfaces on Earth, yet their emptiness is deceptive. Beneath the sediment lie ancient features, buried volcanoes, ridges and fractures. On their surface lie manganese nodules, mineral-rich lumps that have attracted interest for deep-sea mining. Life here is sparse compared to shallower waters, but not absent. Strange creatures adapted to low-energy environments wander slowly, feeding on the trickle of organic material falling from above. The plains remind us that architecture is not always vertical. Sometimes it is horizontal, vast and seemingly endless. Hydrothermal vent fields, often located along mid-ocean ridges, add another layer of complexity. These are places where seawater seeps into cracks, heats up by magma, and bursts back out rich in minerals. The minerals precipitate into chimneys that rise like spires, some taller than houses. They are not mountains in the traditional sense, but they are part of the seafloor's architecture, growing and collapsing in cycles, reshaping landscapes in miniature. Around them, life gathers in abundance, forming oases in the deep. The architecture here is both geological and biological, shaped by chemistry as much as by tectonics. One of the most humbling aspects of this architecture is its invisibility. On land, mountains inspire awe because we see them. They tower over us, visible reminders of Earth's power. Underwater, the same mountains exist, but we rarely imagine them. Few people, when thinking of the Himalayas, also picture the undersea ridges that dwarf them in length. Few realise that most volcanic activity on Earth happens not in familiar mountains like Vesuvius or Fuji, but in submarine volcanoes erupting unseen. The architecture of Earth is weighted toward the ocean, but our imagination remains fixed on land. This hidden architecture also plays a central role in Earth's systems. Mid-ocean ridges release heat and chemicals that influence ocean chemistry. Trenches recycle crust into the mantle, driving plate tectonics. Seamounts redirect currents, creating upwellings that fertilize surface waters. Even abyssal plains, flat as they seem, record Earth's history in layers of sediment, capturing climate cycles, extinctions, and cosmic impacts. The ocean floor is not just a backdrop. It is an active participant in planetary processes. To ignore it is to miss the foundation of Earth's story. Exploration of this architecture remains fragmentary. Submersibles have visited trenches only a handful of times. Seamounts are often discovered accidentally when ships pass overhead. Abyssal plains have been sampled at only a few points, their vastness otherwise untouched. The ridges, though studied in parts, remain mostly unmapped in detail. Every new survey reveals features we did not expect. New volcanoes, new vents, new fault systems. It is as if we are still in the age of early terrestrial exploration, when entire continents were being sketched for the first time. The ocean floor is our last great terra incognita, a map still waiting to be drawn. Part of the awe comes from realizing how dynamic this architecture is. Mountains rise and erode on land over millions of years. On the seafloor, new crust forms continuously. Trenches swallow it. Volcanoes erupt. Vents collapse. Sediments settle. The architecture is alive in geological time, reshaping itself constantly. Earth's surface is not static. It breathes, moves, and shifts beneath the water, reminding us that the ground beneath our feet is temporary, part of a cycle driven by forces we cannot see directly. For explorers, glimpsing this architecture is transformative. Pilots of submersibles describe descending into canyons that vanish into darkness, their walls stretching upward out of sight. Scientists aboard research vessels describe the shock of sonar revealing seamounts taller than any building rising from nothing. Divers near shallow volcanoes describe the strange feeling of standing on slopes that continue down into blackness, knowing that the mountain beneath them is far larger than the island above. These are encounters with the true scale of Earth, hidden but undeniable. The architecture also shapes imagination. Myths of undersea kingdoms, lost continents, and monsters often reflect subconscious awareness of landscapes we could not see. The idea of Atlantis, a city swallowed by the sea, echoes the reality of submerged plateaus and drowned coastlines. The fear of trenches as bottomless voids echoes the true depth of places like Mariana. Even today, stories of undersea volcanoes erupting with enough power to change weather capture attention because they reveal how much happens beneath our awareness. The architecture of the planet is not silent. It intrudes into our lives through earthquakes, tsunamis, and climate shifts, whether or not we choose to look at it directly. In a sense, the ocean's hidden architecture is a reminder of humility. We walk on land and think we understand Earth. We point telescopes at Mars and think we know other planets. But beneath our own seas lies a world larger, taller, deeper, and more active than almost anything we've mapped elsewhere. It is our foundation, our planet's skeleton, and yet it remains largely unseen. To truly explore the ocean is to confront this architecture, to accept that Earth is not just the ground beneath our feet, but the ground beneath the waves. And so, having traced these ridges, trenches, and plains in our imagination, we return to the human perspective. For while these structures are awe-inspiring, they also confront us with feelings we rarely discuss. To stand at the edge of a trench in a submersible, to drift above a seamount in darkness, to hear the creaks of a hull in the silence of the abyss, these are not just scientific moments, they are psychological ones. The ocean's architecture does not just challenge our tools, it challenges our minds. And that brings us to the next barrier, not of geology or engineering, but of the human psyche. The fear, loneliness and strangeness of entering an environment so vast and indifferent. The ocean is not just a physical barrier, it is also a psychological one. For every obstacle of pressure, cold or darkness, there is an equal obstacle in the human mind. The unease of isolation, the dread of the unknown, the quiet fear of being surrounded by endless weight and endless blue. To understand why we cannot truly explore the ocean, it is not enough to talk about geology or engineering. We must talk about psychology, because the mind carries limits as real as any hull or oxygen tank. On the surface, the sea inspires calm. People sit on beaches, watching waves roll in, listening to the rhythm of water against sand. The horizon stretches wide, and the openness feels freeing. But the moment you leave the surface, that openness turns into something else. Descend just a few meters and the world closes in. The light dims, the sounds shift, the water presses. Look around, and you see nothing but blue fading into darkness. There is no horizon, no sky, no landmarks. The human brain, tuned for land with its points of reference, begins to feel unmoored. It is not just disorientation, it is a creeping sense of being in a place that does not belong to you. Divers often describe this sensation as both beautiful and unsettling. In the shallows, the water is bright, filled with life, coral and colour. But push deeper and the beauty thins. Shadows grow, sounds distort. The world feels empty. Some people thrive in that emptiness, calling it peaceful. Others feel unease growing with every metre, a primal discomfort that is hard to name. It is not claustrophobia, because the space is infinite. It is not agoraphobia, because the space is enclosed. It is something in between, a unique psychological space where the mind cannot categorize what it is experiencing. That unease deepens when true darkness comes. In a submersible, as you pass the last reach of sunlight, you're surrounded by blackness so complete that your eyes strain in vain. Turn off the lights, and the void is absolute. This is not like closing your eyes in a dark room, because even then your ears hear walls, your skin senses boundaries. In the deep ocean, there are no boundaries to sense. The darkness is infinite in every direction, and the only certainty is that it is filled with water pressing against you. That realization can trigger panic. The mind begins to conjure shapes, to imagine movement in the black. Even trained explorers describe feeling watched, surrounded, though instruments register nothing nearby. Loneliness is another weight. In space, astronauts feel isolation, but they also see Earth shining below, a reminder of connection. In the deep ocean, there is no such view. Once the hatch closes and descent begins, contact with the outside world grows faint, distorted by slow acoustic signals. You sit in a small sphere with one or two companions cut off from the rest of humanity, surrounded by silence that is not silence at all. The groans of the hull, the distant pops of shifting water, the faint hum of machinery, all serve as reminders that you are alone in a place that does not care if you survive. Loneliness here is not just the absence of people. It is the awareness of being beyond reach, beyond rescue, beyond recognition. Fear, too, takes on new forms. On land, fear usually has an object, a predator, a storm, a cliff edge. In the deep ocean, fear is ambient. It is the knowledge of pressure waiting to crush if a seal fails. It is the awareness that no one can reach you if systems break. It is the uncertainty of what might drift out of the dark, whether creature or current. This fear is not sharp, but dull, gnawing, steady. It is the background hum of every moment spent below. Experienced explorers learn to manage it, to keep focus on tasks, but it never fully leaves. The ocean always whispers that you do not belong. Even those who never descend feel echoes of this psychology. Stories of shipwrecks, lost submarines, or deep-sea disappearances stir imaginations. Myths of monsters lurking in trenches resonate because they speak to something primal. The fear of drowning, of being swallowed by water, is one of humanity's most ancient. The ocean magnifies that fear by multiplying it across scale. Not just drowning in a river or lake, but drowning beneath kilometers of water, lost in an endless expanse. The psychological barrier is not limited to those who go down. It permeates cultures, shaping how we imagine the sea. For scientists and explorers, acknowledging this barrier is part of preparation. Training for deep-sea missions involves not just technical skills, but psychological resilience. Submersible crews must remain calm in confined spaces for hours, maintaining composure when instruments fail or conditions worsen. Divers practice managing panic responses, slowing their breathing, keeping rational thought in situations where instinct screams to flee upward. This training works, but it also reveals how fragile the mind is when confronted with alien environments. The ocean does not just test machines, it tests resolve. There is also the effect of scale. On land, landscapes have limits. A mountain ends at its summit, a desert at its edge. In the ocean, scale is unbounded. You can dive for hours and still not touch bottom. You can drift in any direction and find only more of the same. That sense of endlessness can overwhelm. It erodes the mind's ability to hold perspective. People describe feeling both insignificant and exposed, as if the ocean is too large to comprehend and yet entirely surrounding them. This paradox, of being lost in something boundless yet trapped within it, creates a unique psychological pressure. It weighs not in tons per square inch, but in thoughts per second. Some explorers find meaning in this. They describe it as humbling, even spiritual, a confrontation with something greater than themselves. Others find it destabilizing, even haunting, a reminder of human fragility. Both reactions speak to the same truth. The ocean is not just a place. It is an experience of scale and indifference that reshapes how people think. To truly explore it would mean not only surviving physically but also adapting mentally, learning to exist in a state of awe, fear, and solitude without breaking. The psychological ocean extends beyond individuals. It shapes societies too. Nations hesitate to invest heavily in deep exploration partly because the ocean feels forbidding. Space inspires dreams of new frontiers, colonization, even hope for humanity's future. The ocean inspires caution, dread, even avoidance. Its mysteries are framed less as promises than as threats. That cultural psychology influences where resources go, and so the deep remains unexplored, not just because of cost or technology, but because of collective hesitation. And yet, we cannot ignore it. The ocean surrounds us. Its moods affect our weather, its currents shape our climate, its ecosystems feed us. To treat it only as fearsome is to miss its central role in our lives. The psychological barrier, then, is not meant to stop us but to remind us. The ocean demands respect. It forces us to confront limits, to admit fragility, to balance curiosity with humility. These are not comfortable lessons, but they are necessary. Explorers who return from the deep often describe lasting effects. Some speak of recurring dreams of darkness and weight, others of renewed appreciation for air and light. Some describe the experience as addictive, the strangeness pulling them back again and again. Others describe it as something they endured once and never wish to repeat. The ocean leaves its mark on the mind, shaping memories as powerfully as it shapes landscapes. Ultimately, the psychological ocean is as real as the physical one. Fear, loneliness, and endless blue are not side effects of exploration. They are part of the terrain. To explore the ocean fully would mean not just building stronger machines, but stronger minds. Minds capable of dwelling in alien silence without breaking, capable of facing indifference without despair. Until then, the psychological barrier remains one more reason why we cannot truly explore the sea. And yet, even as we consider these mental challenges, we must also remember how fragile the frontier itself is. For all its power and immensity, the deep ocean is vulnerable to us. Exploration brings risk not only to explorers, but to the environments they study. The next step in this journey is to consider that fragility, the paradox that the ocean, which feels indestructible, is in fact delicate, and that our attempts to explore can sometimes do harm to the very mysteries we wish to protect. When people imagine the deep ocean, they often picture it as untouchable. It seems too vast, too remote, too powerful for humans to truly affect. The pressure alone feels like an eternal defense. The darkness, like a barrier we could never cross. The scale too large for us to leave more than a scratch. Yet this impression is misleading. For all its immensity, the ocean is fragile. Its ecosystems are delicately balanced. Its creatures finely tuned to extreme conditions. Its processes easily disturbed. And the irony is that exploration, the very act of trying to study and understand it, can sometimes cause harm. The frontier is fragile, and every step we take into it carries risk, not only for us, but for the world we're trying to explore. One way to understand this is to look at how life in the deep survives. In shallow waters, ecosystems recover quickly from disturbances. Coral reefs may take decades to heal, but they still respond to light, currents, and abundant nutrients. On land, forests can regrow after fire, grasslands can recover after drought. In the deep, however, life moves on a slower clock. Temperatures are near freezing, food is scarce, and growth is painstakingly slow. Corals that line the slopes of seamounts can be centuries old. Some deep-sea sponges live for thousands of years. Even fish grow and reproduce at a slower pace. Disturbances here are not healed in years or decades. They linger for centuries, sometimes millennia. This is why exploration must tread carefully. A trawl net dragged across a deep-sea coral bed can wipe out ecosystems that took hundreds of years to form. A remotely operated vehicle hovering clumsily can damage fragile structures with a misplaced thruster. A sampling device scraping the seafloor can disrupt sediments that have been stable for ages. Even lights and noise, harmless in shallow environments, can disturb creatures that have never evolved to deal with sudden brightness or mechanical sound. What feels small to us can be catastrophic in an environment so delicately balanced. Then there is pollution. Every expedition carries equipment, fuel, and waste. Most crews are careful, but accidents happen. Oil spills, discarded plastics, lost instruments, all can end up settling in the deep. Because there is little circulation, pollutants can remain for centuries, slowly breaking down, slowly spreading through food webs. Studies have already found microplastics in the stomachs of amphipods from the deepest trenches, creatures that live where sunlight has never reached. This shows how even in direct human presence, pollution carried from far away can penetrate the most remote corners of the ocean. Exploration is not isolated from this problem. By sending ships and machines, we contribute to the same trail of debris. Mining adds another layer of concern. The deep seafloor holds minerals, manganese nodules, cobalt crusts, rare earth elements that companies hope to harvest. To explore these possibilities, they send down survey vehicles, scraping samples, dragging sensors, testing equipment. Even at the exploration stage, this activity disturbs habitats. Nodules form over millions of years, growing millimetre by millimetre. Around them live creatures uniquely adapted to those surfaces. Remove or disturb them, and you erase not just a resource but an ecosystem. Once removed, it will not return within any human time frame. Exploration here risks turning fragile habitats into laboratories for extraction, rather than sanctuaries for knowledge. There is also the risk of unintended consequences. When explorers find hydrothermal vents, they are often tempted to sample them heavily. Tube worms, clams, crabs and bacteria are collected in large numbers for study. This provides valuable science, but it can also destabilize vent communities. Some vents are small, localized ecosystems, remove too much, and the balance collapses. What was meant to reveal knowledge can end up destroying the very system it sought to understand. The fragile frontier does not always recover from our curiosity. Noise from exploration poses another invisible danger. Sonar is one of the most valuable tools for mapping and navigation, but its signals can interfere with marine mammals that rely on sound. Whales and dolphins have been known to strand themselves following exposure to intense sonar. Even lower-level noise can disrupt communication, feeding, or migration. While ships and submarines do not intend to cause harm, their presence creates a sound footprint that ripples through the ocean's acoustic world. For creatures dependent on hearing, this intrusion can be as disruptive as pollution. Exploration brings with it sound, and sound can carry consequences far beyond the reach of human intention. The fragility of the frontier becomes clearest when we realize how little margin for error exists. In robust ecosystems, mistakes can be absorbed. In fragile ones, mistakes echo. A single misstep can undo centuries of growth, and because we know so little about the deep, we often cannot predict what damage we might cause. We may trawl across a plain thinking it barren, only to destroy unique species we had not yet discovered. We may drill into a seafloor vent thinking it minor, only to disrupt chemistry vital to an entire community. Ignorance magnifies fragility. To explore without knowing is to risk destroying before we understand. There is also a paradox at play. To protect the ocean, we must understand it. But to understand it, we must enter it, sample it, and sometimes disturb it. This tension lies at the heart of modern oceanography. Scientists wrestle with how to balance curiosity with caution, knowledge with preservation. Do we dive into fragile habitats to study them, or leave them untouched and unknown? Do we take specimens for labs, or rely only on observation? Every decision carries trade-offs, and there are no easy answers. Exploration is never neutral, it always leaves traces. At the same time, exploration can bring awareness that leads to protection. Without the discovery of deep-sea corals, few would know to advocate for their conservation. Without images of hydrothermal vent life, few would care about the ecosystems threatened by mining. The act of revealing fragility can be the first step towards safeguarding it. But this only happens if exploration is careful, respectful, and mindful of consequences. If not, it risks being another form of exploitation disguised as science. This fragility extends even to cultural perception. The ocean has long been imagined as endless and indestructible. Shifting to the idea of fragility requires a mental adjustment. When explorers share stories of delicate coral beds, of vents teeming with unique life, of trenches filled with microplastics, they chip away at the myth of invulnerability. This awareness changes how societies think, how policies form, how industries operate. Exploration, then, is not just about data. It is about reshaping understanding. convincing people that what seems eternal is in fact vulnerable. The fragile frontier is also personal. Explorers themselves feel responsibility when they witness harm. Pilots of submersibles have described regret after accidentally striking fragile structures with thrusters. Scientists recall the guilt of realizing that their collections may have reduced a rare population. Divers describe the sadness of watching once thriving reefs fade after repeated visits. These emotions reflect an awareness that exploration is not innocent. Every act of looking carries the possibility of altering. The ocean demands humility in response. As we think about this, the frontier becomes more complex. It is not just a barrier to cross, not just a space to conquer. It is a relationship. Our presence changes it, and in changing it, we change ourselves. To truly explore the ocean would mean not only developing stronger machines or braver minds, but also deeper ethics, an ability to weigh curiosity against care. Without that, exploration risks becoming exploitation, and the fragile frontier risks becoming a ruin rather than a revelation. And so, having lingered on fragility, we turn naturally to how humans have always filled gaps in understanding with imagination. Before we had cameras in the deep, we had stories. Before we had sonar, we had myths, and those myths, often filled with monsters and mysteries, reflected not only ignorance, but also respect. They showed that people sensed fragility and danger, long before science confirmed it. From fragile reality, we drift next into imagination, to see how the ocean has lived in human minds as a place of myths and monsters, a realm that mirrors both fear and wonder. For as long as humans have looked at the sea, they have filled its depths with creatures of imagination. Before sonar and submersibles, before scientific charts and photographs, the ocean was a mirror for our fears and fantasies. Sailors staring at endless horizons wondered what waited beneath the waves. People living on coasts heard strange sounds from the surf, found enormous bones or carcasses washed ashore, and tried to explain them. In every culture touched by the ocean, myths of monsters emerged. These stories were not simply entertainment. They were attempts to give shape to the unknown, to make sense of the mystery of a world that felt both essential and terrifying. In ancient times, the ocean was imagined as a realm of gods and beasts. The Greeks spoke of Poseidon, ruler of the sea, whose moods brought storms and calm. They told of sea serpents coiled beneath the waves, of Scylla and Charybdis lurking near straits, ready to devour sailors who strayed too close. The Norse spoke of Jörmungandr, the Midgard serpent, so vast it encircled the world. In Polynesian traditions, ocean deities shaped islands and guided voyagers, embodying both danger and sustenance. These myths reflected the double nature of the ocean. It gave life through fish and trade, but it also took life through storms and shipwrecks. To imagine it as populated with monsters was to give it personality, to acknowledge that it could not be trusted or fully known. As exploration expanded, so did the catalogue of creatures. Medieval maps of the world often included drawings of sea monsters in the margins, fish with human faces, dragons with fins, whales large enough to be mistaken for islands. These images were not idle decoration. They served as warnings, visual reminders that the ocean was full of hazards. To a sailor venturing into the unknown, the thought of serpents and leviathans was no less real than the threat of storms. Fear of monsters became a way to embody the unpredictability of the sea itself. The kraken is one of the most enduring of these myths, described in Scandinavian stories as a giant octopus or squid, large enough to drag ships under. It haunted sailors' imaginations for centuries. Reports of huge tentacles rising from the water, or of whirlpools formed by its descent, circulated widely. We now know that giant squids do exist, reaching lengths of over 10 meters, and colossal squids even larger. Though these animals are reclusive and rarely seen, they explain how fragments, tentacles found in whale stomachs, carcasses washed ashore, could feed legends. The Kraken was not a fantasy born from nothing. It was a myth built around glimpses of real creatures, amplified by fear and awe. The Leviathan of biblical tradition held similar weight, described as a monstrous sea serpent, untamable and immense. In Jewish, Christian and Islamic texts, it symbolized chaos, the uncontrollable force of the deep. Its presence in scripture reflects how universal the ocean's mystery was. Even far from coasts, cultures incorporated sea monsters into cosmology, treating the ocean as a metaphor for the unknown forces that humans could never master. To name those forces as monsters was to acknowledge their power, while also making them part of human storytelling. Sailors returning from voyages often contributed to these imaginations. Tales of mermaids, half human and half fish, were common. Some accounts likely stemmed from sightings of manatees or dugongs, animals that from a distance might resemble human forms. Others may have arisen from dreams and hallucinations during long, exhausting journeys. Mermaids were not always benign. In many stories they lured sailors to their deaths, representing both temptation and danger. They captured the contradictory feelings the sea inspired: attraction and fear, beauty and destruction. Even in the modern era, myths persist. Reports of sea serpents surfaced in the 19th century, fueled by encounters with oarfish, long ribbon-like fish that can grow over 10 meters and occasionally wash ashore. Sightings of strange lights in the water, likely bioluminescence, were described as glowing monsters. Submarine crews in the World Wars sometimes reported shapes they could not identify, shadows moving through sonar, noises unlike anything they had heard before. The ocean, even with technology, continued to resist explanation, and so imagination filled the gaps. These myths are not simply curiosities. They reveal how humans grapple with ignorance. When faced with the unknown, we project familiar patterns, animals larger, stranger, or more dangerous than those we know. The ocean, with its vastness and inaccessibility, became the perfect canvas. Myths allowed people to talk about the sea's unpredictability without reducing it to mere weather or chance. Monsters were metaphors for danger, reminders that humility was necessary in the face of the deep. Science has not erased these myths but transformed them. The discovery of giant squid in their natural habitat confirmed part of the Kraken legend. The finding of deep-sea creatures with bizarre shapes, fish with transparent heads, eels with massive jaws, jellyfish glowing like lanterns, feeds imaginations even today. Photographs from deep dives are shared widely not just because they are scientific, but because they feel mythic, like glimpses of creatures from stories made real. The line between myth and discovery blurs, showing that imagination and exploration are not opposites but companions. Culturally, the ocean remains a stage for monsters. Literature and film have embraced this, from Melville's Moby Dick, with its white whale as a symbol of obsession and fate, to modern films that cast the ocean as a realm of terror. Jaws made people fear sharks more than statistics warranted. Science fiction stories imagine hidden civilizations beneath the waves, lost cities like Atlantis waiting to be uncovered. These cultural creations shape public perception as much as science does. The ocean in imagination is never empty. It is always populated, always alive with presences that challenge and threaten us. Even in dreams, the ocean takes on monstrous qualities. Psychologists note how water often symbolizes the subconscious, vast and uncontrollable. To dream of drowning, of being pursued by sea creatures, of being lost in endless blue, reflects anxieties that the waking mind cannot articulate. The ocean becomes a symbol of the unknown within ourselves, and monsters embody fears we carry but do not name. Myth, in this sense, is not just about the sea, it is about the human mind using the sea as a mirror. This mirror continues to reflect as exploration advances. When James Cameron descended into the Mariana Trench, many headlines invoked the Kraken. joking about what might rise from the depths. When researchers release new footage of strange fish or jellyfish, the language often turns mythic, alien, monstrous, otherworldly. Even with science at the forefront, myth lingers as the language we use to make sense of strangeness. The deep ocean does not need monsters invented. Its real inhabitants are mythic enough. But myths also serve a purpose in keeping attention alive. People may not be inspired by sonar maps of ridges, but they are captivated by stories of glowing creatures or giant squids. The mythic framing draws people in, giving science a narrative hook. The challenge is to balance awe with accuracy, to use imagination without letting it distort reality beyond recognition. Because the ocean's true fragility, as we saw before, can be obscured if we focus only on monsters and forget ecosystems. Yet imagination is unavoidable. The ocean demands it. Its hidden architecture, its strange creatures, its resistance to being fully known. These invite storytelling. Myths of monsters are not distractions. They're expressions of curiosity, fear, and wonder. Emotions as much a part of exploration as instruments and funding. They remind us that the unknown is not empty but full, not silent but resonant, not inert but alive in both fact and imagination. And as we leave the world of myths, we must return to the reality of change. The ocean is not static, not eternal. It is shifting even now, under the influence of climate change, warming, acidification, and rising seas. The frontier is not only fragile in the sense of being delicate, it is also fragile in the sense of being in flux, changing faster than our ability to study it. Myths once gave the ocean timelessness. Science now reminds us of its impermanence. From monsters of imagination, we move toward the reality of climate and the way it is reshaping the unknown, before we have had the chance to fully explore it. For centuries, the ocean seemed eternal. Its tides came and went, its storms rose and faded, its waves broke endlessly on the shore. People thought of it as a constant, a backdrop to human history that did not change in any fundamental way. Empires rose and fell, cities were built and abandoned, but the sea remained. Yet now, in the span of a single lifetime, that illusion has begun to break. The ocean is changing, and not slowly in geological time, but quickly, within human memory. Climate change is rewriting the rules of the sea, and in doing so, it is shifting the very borders of the unknown. Rising seas are the most visible sign. As ice sheets melt and glaciers retreat, as water expands with heat, coastlines creep inland. Islands that seem secure are now threatened. Villages built near shorelines face flooding, and cities designed with one tide line in mind find that line advancing relentlessly. The ocean is no longer a boundary we can take for granted. It is encroaching, claiming land, redrawing maps. The border between land and sea, once thought fixed, is proving to be temporary. This alone reshapes how we think about exploration, because the unknown is no longer only out there in the deep. It is arriving at our feet, changing the familiar into something strange. But the deeper changes are less visible. The ocean absorbs most of the excess heat trapped by greenhouse gases. It has taken in over 90% of that energy, becoming a vast reservoir of warming. This heating changes currents, alters weather, and shifts ecosystems. The great conveyor belt of circulation, the system that moves warm and cold water around the globe, is slowing in places, accelerating in others. These changes ripple outward into climate patterns on land, into storms, rainfall, and droughts. The ocean is not only rising, it is stirring in new ways, unpredictable ways, making the unknown not just a matter of geography but of time. What will the sea be like decades from now, and how will it shape everything above it? Acidification adds another dimension. The ocean absorbs carbon dioxide as well as heat, and in doing so its chemistry changes. The pH shifts, becoming more acidic, and creatures that rely on calcium carbonate, corals, shellfish, plankton, struggle to build skeletons and shells. Reefs that once flourished are bleaching and dying, their vibrant communities collapsing into rubble. At depth, shells dissolve more easily, altering food chains. This chemical transformation reaches even into the trenches. What was once stable is becoming unstable. What was once predictable is becoming fragile. The ocean is not just water, it is chemistry in flux, a vast experiment we are running without full control. All of this complicates exploration. The unknown we hope to study is not waiting patiently. It is changing even as we try to reach it. By the time we map a reef, it may already be dying. By the time we catalogue a species, its habitat may be vanishing. The ocean is shifting beneath our instruments, demanding speed we do not have. What was once a frontier of timelessness is becoming a frontier of urgency. Exploration is no longer only curiosity. It is triage, a race to record before loss. Rising seas reshape culture as well as science. Stories of coastal communities are being rewritten. In the Pacific, entire islands face disappearance, and with them languages, traditions, and ways of life tied to place. In the Arctic, ice routes once impassable are opening, altering trade and geopolitics. In deltas, saltwater intrudes into farmland, changing diets and economies. The ocean's edge is not just a physical border, it is a cultural one, and as it shifts, human identity shifts too. Exploration, in this sense, is not optional, it is forced. People must explore new ways of living with a sea that no longer stays in place. The rising ocean also redefines risk. Storm surges ride on higher baselines, flooding farther inland. Hurricanes gather more energy from warmer waters, striking with greater intensity. Tsunamis, triggered by undersea earthquakes, ride on seas already elevated. The border of the unknown now includes disasters amplified by climate. The frontier we cannot fully chart is also the frontier that threatens us more directly. To ignore exploration is to risk surprise at scales we cannot afford. Yet the paradox deepens. The very act of exploring requires ships that burn fuel, equipment that consumes resources, institutions that leave carbon footprints. Exploration seeks to understand change but is also entangled in it. The question becomes not only how to study the shifting ocean, but how to do so without worsening the shifts. Sustainability becomes part of the frontier. To study the ocean ethically now means to design exploration that minimizes harm while maximizing knowledge. It is no longer a pure pursuit of curiosity, it is negotiation with responsibility. There is also the matter of perception. For centuries, myths cast the ocean as timeless. Climate change is shattering that narrative, but public imagination lags. Many still see the sea as unchanging, eternal, immune. Exploration, then, must serve not only science, but communication. To show people that the ocean is fragile, to make them understand that it is changing rapidly, is as important as measuring currents or cataloguing species. Without that awareness, the urgency of exploration will not translate into action. The unknown will remain distant in minds, even as it rises onto doorsteps. For those who venture into the deep today, the shift is tangible. Submersible pilots describe seeing plastic bags at depths where no human has ever swum, reminders that surface activities reach even here. Scientists studying corals document not just new species but bleaching and death. Data points in a story of loss. Divers exploring reefs describe landscapes transformed within their lifetimes, vibrant one year, barren the next. These personal accounts echo the broader data. The ocean we are trying to explore is not waiting. It is moving faster than our tools, and still, the allure remains. Exploration continues not only because of urgency, but because of wonder. Even as reefs bleach, new species are discovered. Even as seas rise, deep trenches reveal mysteries. The ocean resists being reduced to crisis alone. It is fragile, it is changing, but it is also vast, filled with life and landscapes that inspire awe. Exploration, in the age of climate change, carries both grief and hope. It becomes not only a search for knowledge, but a search for meaning in a world we are altering. The rising sea also connects us more deeply to other frontiers. Climate change blurs the line between ocean and atmosphere, between biology and geology. Melting ice alters salinity, which alters circulation, which alters climate on land. The borders of the unknown are not confined to the deep. They reach into weather, agriculture, politics, migration. To explore the ocean now is to explore a web of consequences that touch every part of human life. The frontier is no longer remote, it is everywhere. In this way, the unknown is shifting not only outward but inward. The ocean has always been a mirror of imagination, but now it becomes a mirror of responsibility. The monsters we once placed in it were symbols of fear. The changes we now measure in it are reflections of ourselves. Rising seas and warming waters are not alien forces, they are the results of human action. The unknown we confront is not simply the ocean's mystery, it is our own future, refracted through water. And so, as we drift from this recognition, the story bends again. For if climate change makes exploration urgent, it also makes us reconsider the boundaries of what exploration means. It is no longer only about ships and submarines. It is about satellites tracking currents, communities adapting to tides, policies deciding how coastlines are defended. Exploration has become planetary, a collective act of adjusting to a shifting sea. To understand this shift fully, we must look at how human activity and ocean systems are entangled, how industry, trade, and consumption extend their reach beneath the waves, and how the unknown is no longer purely natural but increasingly human-made. For most of history, the idea of exploring the ocean meant people descending into it. Divers with simple masks, sailors venturing further from shore, submersible pilots sealed into cramped spheres. Human bodies were at the centre of exploration, fragile yet determined. But as the barriers of pressure, darkness, and scale became clearer, so did the limits of that approach. The future of ocean exploration now seems to belong not to fragile travellers in suits or submarines, but to machines built to do what we cannot: survive indefinitely, move freely, and process information faster than we ever could. Robots and artificial intelligence are emerging as the new explorers of the sea, carrying our curiosity into places we may never physically reach ourselves. Already this shift is visible. Autonomous underwater vehicles roam sections of the ocean with no tether, gliding silently through currents, mapping terrain with sonar, taking samples, and recording video. Some are shaped like torpedoes, streamlined for range and endurance. Others resemble gliders, adjusting buoyancy to move up and down through the water column slowly but efficiently. These machines can cover distances far greater than any diver or submersible, staying below for weeks or months before surfacing to transmit data. They are not dependent on oxygen, not vulnerable to panic or fatigue. They extend the human presence into environments where human presence is nearly impossible. Remotely operated vehicles remain equally important. Tethered to ships by cables that provide both power and communication, they allow scientists to explore in real time, steering robotic arms, zooming cameras, and maneuvering thrusters from the safety of the surface. These machines bring the deep into labs aboard ships, making it possible for teams to watch and react without ever descending themselves. Their arms collect samples of corals, their cameras capture strange creatures, their sensors record data on chemistry and physics. They represent the compromise between autonomy and control, between distance and connection. The future pushes both of these further. Advances in battery technology promise vehicles that can stay submerged for months or even years, wandering entire basins without returning to the surface. New materials and designs promise machines that can withstand greater pressures with less bulk, reaching trenches routinely rather than exceptionally. AI offers the possibility of vehicles that are not just pre-programmed but genuinely adaptive. Machines that can recognize when they see something unusual, choose to investigate, and send back only the most relevant information. Instead of sifting through endless terabytes of raw data, scientists might receive curated discoveries made by the machines themselves. The ocean's scale demands such intelligence, because no team of humans could ever process every detail. Robotic swarms are another frontier. Instead of a single expensive submersible covering a small area, fleets of cheaper, smaller robots could spread out, working cooperatively like schools of fish. They could map vast sections of seafloor simultaneously, track migrating animals across oceans, or monitor environmental changes in real time. Coordinated by AI, such swarms could adapt dynamically, clustering around points of interest, dispersing to cover ground, relaying information across networks. This would transform exploration from a slow, piecemeal process into something continuous and expansive. Above the surface, satellites will remain essential partners. They cannot see through water, but they can track its surface height, temperature, and colour, inferring much about what lies beneath. Combined with robotic fleets below, they create a two-layered system, one watching from above, one from within. Together, they would provide a level of coverage we have never had before. The unknown would not disappear, but it would shrink. The dark maps would begin to fill in. The role of humans in this future becomes more symbolic. Instead of descending themselves, they descend through proxies. They design, guide, and interpret, but they no longer need to risk their bodies against crushing pressure. For some, this is liberating. It allows exploration to scale in ways impossible before. For others, it is bittersweet. The intimacy of being physically present in the deep, of watching darkness press against a viewport, of hearing the creaks of a hull may fade. Exploration becomes mediated, translated through screens and data streams. The romance of the lone explorer gives way to the efficiency of fleets of machines. Whether this feels like loss or progress depends on how one values presence. AI will not only control vehicles, but also interpret patterns. Already, algorithms are being trained to identify species from video footage, to recognize geological formations, to spot anomalies in sonar data. As these systems improve, they may notice things humans would miss: subtle variations in movement, faint echoes of hidden structures, statistical patterns in environmental data. The ocean's complexity is too vast for human attention alone. AI extends perception, making it possible to grasp connections invisible to unaided minds. In this sense, the future of exploration is not just about machines entering the ocean, but about machines expanding our very concept of what exploration means. There are risks in this reliance. Autonomous machines can fail, wander, or disappear. AI can misinterpret, classify wrongly, or miss what matters most. Trusting machines to carry exploration means accepting that we may lose some control, some directness. Ethical questions also arise. If robotic swarms can extract samples at scales far greater than before, how do we ensure they do not damage fragile ecosystems in the process? If AI chooses what to report, how do we ensure it does not filter out discoveries that matter? The same qualities that make machines powerful also make them unpredictable, and the ocean's fragility demands caution. Still, the momentum is clear. The cost of manned missions is immense, while the cost of robotic missions continues to fall. Governments, universities, and even private companies are investing in fleets of robots, seeing them as scalable, sustainable, and effective. The future of ocean exploration will likely resemble the future of space exploration. Robots first, robots always, with humans participating mainly as controllers and interpreters. The dream of colonizing the sea, of living in underwater cities, may remain a fantasy. The practical reality will be robotic presence, human absence. And yet absence is not emptiness. Humans will still be there, in the design of the machines, in the questions asked, in the interpretations made. exploration is never purely about presence. It is about knowledge, and knowledge can be transmitted through any medium. The ocean may never know or care whether it is observed by a diver, a submersible pilot, or a fleet of drones. For the ocean, observation is observation. For us, the meaning lies in how we connect to what is discovered. Robots do not replace curiosity, they extend it. The horizon of new frontiers is vast. Imagine networks of sensors embedded across the seafloor, continuously measuring currents, chemistry, and tectonic movement. Imagine AI systems tracking whale migrations in real time, correlating them with climate data. Imagine fleets of drones patrolling trenches, recording volcanic eruptions and vent activity as they happen. Imagine robots carrying labs within them, analysing samples instantly rather than returning them to ships. These visions are not distant science fiction. They are plausible extensions of technologies already in development. The future of exploration is not just descent. It is integration, a web of machines and minds spread across the sea. And even as machines take over much of the work, humans will still descend occasionally, not because it is efficient, but because it is meaningful. Just as astronauts still travel to space despite robots being more practical, divers and explorers will still seek the deep for the experience itself. To sit in darkness, to feel the ocean press around you, to see with your own eyes what no one has seen before, this cannot be replaced. Robots may carry the bulk of exploration, but humans will remain its storytellers, carrying back not only data but emotion, not only facts but meaning. The ocean, then, will not be conquered by machines. It will be opened by them, slowly, carefully, incompletely. For all the advances, mysteries will remain. The ocean is too vast, too strange, too dynamic to ever be fully known. AI and robots will expand the frontier, but they will not erase it. They will give us new ways of looking, new ways of listening, but the unknown will endure, shifting always beyond the reach of complete knowledge. That endurance is not a failure of technology, it is the essence of the ocean itself, and so, as we look ahead, we see a future where exploration is no longer a heroic dive into darkness by a few, but a constant network of observation by many. The frontier becomes less about singular feats and more about collective systems. But beneath that future lies the same truth as always. The ocean resists being fully known. Robots and AI may push the border outward, but mystery remains, and mystery is what keeps us looking. From this vision of technology and new frontiers, we drift naturally toward the last question of all, not what the ocean holds, but what it means for us to keep seeking, to keep asking, and to keep wondering why we look into the deep at all. For all the effort we've spent talking about pressure, darkness, cold, cost, technology, and imagination, the ocean remains what it always was, a mystery. Every fact we've gathered, every sample, every sonar map, every dive, is still only a fragment. The unknown stretches wider than the known, and perhaps it always will. That may be the point. To expect the ocean to give up all its secrets would be to misunderstand it. It is not a vault to be emptied. It is a mirror that reflects back our own limits, our own longings, and our own dreams. When we imagine the deep, we are imagining ourselves as much as the water. Our fear of drowning, our fascination with monsters, our urge to map, our push to send machines where bodies cannot go, all of it says as much about what we are as about what the ocean is. It becomes a stage on which human qualities play out. Courage and caution, wonder and greed, humility and ambition. The ocean is vast enough to hold them all. That is why it has always served as a mirror for civilization, showing us who we are at the same time as it hides what it contains. For some, the ocean is a dream of escape. Writers and thinkers imagine leaving behind the constraints of land, sinking into a world that feels both alien and infinite. Science fiction fills its depths with cities, utopias, and new beginnings. For others, the ocean is a dream of terror, a nightmare of drowning, monsters, and endless weight. These dreams, opposite as they seem, are both true. The ocean can be nurturing and terrifying, giving and taking, generous and merciless. To dream of it one way or the other is to capture only a fraction. The whole truth lies in holding both. As explorers, we are drawn not just by facts but by feelings. Scientists measure currents, map ridges and sample chemistry, but many of them admit that what drew them in the first place was awe. The first time they saw a strange fish glowing in the dark, or the first time they watched a hydrothermal vent spouting like an undersea geyser, they felt something beyond data. They felt connection, wonder, humility. Those feelings fuel the work as much as funding or instruments. Without them, exploration would be empty. The ocean is not just an object of study, it is an experience of mystery. Mystery itself is valuable. In a world increasingly mapped, catalogued and measured, the ocean resists completion. It insists that there are still frontiers, still questions without answers, still spaces that cannot be turned into tourist attractions or catalogue entries. This resistance is not frustrating. It is necessary. Humans need mystery as much as they need knowledge. Without it, curiosity fades, imagination dries up, and meaning shrinks. The ocean keeps mystery alive, and in doing so, it keeps us alive in a deeper sense. It reminds us that we have not reached the end of discovery. At the same time, the ocean is practical, grounding us in survival. It regulates climate, produces oxygen, provides food, shapes weather, and anchors economies. It is not only a symbol but a system, not only a dream but a reality. To neglect it, to assume it is too big to fail, is to misunderstand the fragility we have already traced. The dream of the ocean as eternal clashes now with the reality of the ocean as vulnerable. Rising seas, warming currents, and bleaching reefs remind us that mystery does not mean indestructibility. What we fail to care for can be lost, and what is lost may not return. The ocean teaches wonder and warning at once, and so, exploration is both a privilege and a responsibility. To look into the deep is to risk changing it. To sample its creatures is to risk harming them. To map its trenches is to risk forgetting that they are more than data points. The responsibility is to balance curiosity with care, to remember that the unknown is not ours to consume but ours to respect. Mystery is not a weakness to be conquered. It is a gift to be preserved. This duality is why the ocean has always inspired both science and art. Scientists seek to measure it, artists to imagine it, but both respond to the same feeling, that the ocean is larger than us in every sense. Painters have tried to capture its moods, musicians its rhythms, poets its metaphors. Storytellers fill it with monsters and miracles alike. The ocean is muse as much as medium. Its influence on culture mirrors its influence on climate. Quiet, constant, and essential. To remove it would be to remove part of ourselves. Even as robots and AI expand our reach, even as maps grow sharper and data grows deeper, the ocean will remain mysterious. Technology can show us shapes and patterns, but it cannot erase the feelings the deep inspires. A sonar map of a trench does not diminish the awe of knowing it is 11 kilometers deep. A camera feed of a glowing jellyfish does not reduce its strangeness. Mystery is not erased by knowledge, it is deepened by it. The more we learn, the more we see how much remains hidden. The ocean, in this way, is endless, not only in size but in meaning. In the end, perhaps the most important reflection is this: the ocean is not separate from us. It is not an alien world waiting to be conquered. It is part of Earth, part of the system that sustains us. To treat it as other is to misunderstand our place in the web of life. The ocean is not just out there. It is in our weather, our air, our food, our cultures, our myths, our minds. It is mirror and dream, system and story. To look into it is to look into ourselves. And so the closing thought is not an ending but a reminder. The ocean cannot be fully explored, not because we lack courage or technology, but because it will always remain larger than our grasp. That is not failure. That is the essence of mystery. We need frontiers, not only to conquer but to respect, not only to cross but to contemplate. The ocean is one such frontier. It is a mystery we live beside every day, a mirror that shows us both our limits and our possibilities, a dream that pulls us back again and again to wonder. As long as waves break on the shore, as long as currents flow and tides rise, the ocean will remain both familiar and unknown. We may send robots into its depths, we may map its ridges, we may study its chemistry, but we will never reduce it entirely to numbers or names. It will always be more, and in that more lies its true value. Not as something to be finished, but as something to be felt, respected, and remembered. The ocean, then, is mystery, mirror, and dream all at once. It is the unknown we cannot conquer, the reflection of ourselves we cannot avoid, and the dream we cannot stop chasing. That is why, despite the barriers, despite the fragility, despite the cost, we keep looking into the blue, not because we expect to finish the story, but because the story itself is what makes us human.